If you like the space and learn about its curiosities, consider subscribing to the channel. We have 2 videos every week. Thank you for your attention and enjoy the video. Space, the final frontier, as they often say, holds mysteries so vast and profound that even our most advanced technology struggles to comprehend its full scope. Our journey begins here, on Earth, where we gaze up at the night sky, captivated by a sea of stars, each a distant sun with its own story to tell. The vastness of space isn't just a matter of size. It's a challenge to our perception, a place where the rules we know often bend, twist, and sometimes even break. What we know so far is but a speck in an infinite ocean. Yet every discovery reveals a universe stranger than fiction. Humanity has always been fascinated by the night sky, and with good reason. Ancient civilizations like the Babylonians and Egyptians mapped out constellations, using them as calendars and navigation tools. But what they couldn't have imagined is that those tiny pinpricks of light are often millions of light years away, some of them not even existing anymore as we see their light tonight. Our planet, our solar system, and even our galaxy are just small parts of something incomprehensibly vast. Let's start with our closest neighbor, the Moon. A seemingly static and unchanging presence. The Moon is far more complex than we once thought. Did you know that it's slowly drifting away from Earth at a rate of about 1.5 inches per year? This may not seem like much, but over millions of years, it will have dramatic effects on Earth's tides and the length of our days. Scientists believe that billions of years ago, the Moon was much closer, causing massive tidal waves and potentially influencing the evolution of life on our planet. The Sun, the star that gives us life, is another fascinating enigma. It's not just a ball of light and heat. It's a massive nuclear reactor, burning hydrogen at its core and fusing it into helium. This process releases an immense amount of energy. But even more intriguing are the violent solar flares that erupt from its surface, sometimes sending huge amounts of charged particles toward Earth. These solar winds are responsible for the breathtaking auroras at the poles, but they also pose a danger to our technology, as they have the power to disrupt satellites and even electricity grids on a massive scale. Beyond our solar system, things get even stranger. Our Milky Way galaxy alone contains hundreds of billions of stars, each potentially hosting planets that could support life. One of the most incredible discoveries of the past few decades has been the confirmation of thousands of exoplanets, planets outside our solar system. Some of these worlds are hot, barren landscapes scorched by their stars, while others are icy giants with winds that move at thousands of miles per hour. Scientists have even found Earth-like planets in the so-called habitable zone of their stars, where liquid water and potentially life could exist. Black holes are another aspect of space that challenges everything we know about physics. These cosmic giants are regions of space where gravity is so strong that not even light can escape. Once a star collapses under its own gravity, it creates a singularity, a point where space and time cease to exist as we understand them. What lies inside a black hole remains one of the universe's greatest mysteries. Some theories suggest they could be gateways to other parts of the universe or even alternate realities. Recently, scientists captured the first image of a black hole using a network of telescopes around the world, revealing a glowing ring of light surrounding a dark center, a sight both beautiful and terrifying. Speaking of mysteries, dark matter and dark energy make up about 95% of the universe, yet we know almost nothing about them. Dark matter is believed to be an invisible substance that holds galaxies together, while dark energy is thought to be responsible for the universe's accelerating expansion. Without these mysterious forces, our current understanding of physics would collapse. It's as if we're seeing only the tip of an iceberg, with the true nature of the cosmos hidden beneath an ocean of the unknown. Every piece of technology we send into space, from the Hubble telescope to the James Webb Space Telescope, aims to peel back just a bit more of that cosmic curtain. The idea of other life forms is another intriguing aspect of space exploration. With the discovery of extremophiles, organisms that thrive in the most extreme conditions on Earth, like deep-sea vents and frozen glaciers, Scientists believe that life could exist in places once thought impossible, such as beneath the ice-covered oceans of Jupiter's moon Europa or Saturn's Enceladus. Both moons have shown signs of water vapor, indicating that liquid water might exist beneath their icy crusts. If life can thrive in Earth's extreme environments, it raises the tantalizing possibility that something similar could exist elsewhere in our solar system. Even the seemingly simple concept of time gets complicated in space. According to Einstein's theory of relativity, time is not a constant. It warps and bends with gravity. This means that time actually moves slower in stronger gravitational fields, like those near massive planets or black holes. So, if you were to orbit near a black hole for a few years and then return to Earth, you would find that decades or even centuries had passed for those who stayed behind. It's a mind-bending concept that makes time travel a theoretical possibility, although the risks and technical challenges are beyond our current capabilities. The vast distances in space also boggle the mind. Light, the fastest thing in the universe, still takes over 4 years to reach the closest star, Proxima Centauri, from Earth. And that's just within our cosmic neighborhood. To reach the center of our galaxy, the Milky Way, it would take light 25,000 years. The distances between galaxies are even more staggering, with the Andromeda Galaxy, our closest spiral neighbor, located over 2.5 million light-years away. Andromeda is on a collision course with the Milky Way, set to merge in about 4.5 billion years. The result won't be the violent crash one might imagine. Instead, the galaxies will pass through each other, stars rearranging to form a new, merged galaxy. Then, there are the cosmic events that seem to defy explanation. Gamma-ray bursts, for instance, are some of the most powerful explosions in the universe, releasing more energy in a few seconds than our sun will in its entire lifetime. Scientists believe these bursts occur when massive stars collapse or when neutron stars collide, but the exact mechanics remain a mystery. The intensity of these explosions is such that if one happened too close to Earth, it could strip away our atmosphere and cause mass extinction. We also have rogue planets, wandering alone in the darkness of space, not bound to any star. These nomads, torn away from their systems or formed in isolation, could be more common than the stars themselves. Some may even harbor life beneath thick layers of ice, heated by their own internal energy. Without a sun to illuminate them, they travel silently, almost invisible, a reminder of how much we have yet to uncover. The possibility of multiverses takes the strangeness of space to another level. Some theories suggest that our universe is just one of many, each with its own set of laws and conditions. The Big Bang, which we consider the beginning of our universe, could merely be one event in an infinite series of creations and collapses. If true, the implications are staggering. Entire universes could be born and die, and there may be countless versions of reality existing simultaneously, each one beyond our perception. Quasars, the bright beacons found at the centers of some galaxies, shine with the intensity of 1 trillion suns. These energetic objects are powered by supermassive black holes consuming vast amounts of gas and stars. Their light, visible across billions of light years, offers a glimpse into the early universe when galaxies were still forming. The study of quasars helps astronomers understand how galaxies evolve, but it also raises questions about the nature of these ancient cosmic giants and the power they wield. The concept of wormholes, theoretical passages through space-time, also captivates the imagination. If they exist, they could provide shortcuts across vast cosmic distances, allowing for rapid travel between distant parts of the universe. However, creating or stabilizing such a passage would require enormous amounts of energy, potentially even exotic matter with negative mass, something we have yet to confirm or understand. It's an idea that borders on science fiction, yet remains within the realm of theoretical physics. The journey through space is one filled with wonder, danger, and the promise of discovery. From the tiny grains of dust that create meteors in our atmosphere to the massive collisions that birth new galaxies, every aspect of the universe is a testament to the complexity and beauty of existence. As technology advances, so too does our ability to explore these mysteries, pushing humanity further into the unknown. The question is not just what we will find out there, but how those discoveries will change our understanding of who we are and our place in the cosmos. As we venture deeper into the mysteries of space, the concept of alien life continues to captivate both scientists and enthusiasts alike. For centuries, humans have wondered whether we are alone in the universe. The odds seem overwhelmingly in favor of extraterrestrial existence when one considers the sheer number of stars in the universe, each potentially hosting its own system of planets. In recent decades, the search for extraterrestrial intelligence, SETI, has intensified, using radio telescopes to listen for signals from distant civilizations. However, despite our efforts, space remains eerily silent, an enigma that has come to be known as the Fermi paradox. If there are so many stars and planets, where's everybody? One intriguing theory suggests that advanced civilizations might deliberately avoid broadcasting their presence. Perhaps they fear being discovered by hostile entities or prefer to observe other civilizations from a distance, much like scientists observing wildlife without interfering. Another idea is that advanced civilizations might communicate using technologies we cannot yet comprehend, such as quantum communication or methods beyond the electromagnetic spectrum. There's also the possibility that intelligent life, as we know it, might be extremely rare or short-lived. Civilizations may reach a certain level of technological advancement and then face self-destruction through wars, ecological collapse, or catastrophes like asteroid impacts. This could explain why we don't detect any signals. Perhaps other civilizations have existed, but they've either gone extinct or have retreated into hiding, leaving behind no trace. Speaking of catastrophes, our own planet faces several cosmic threats that could dramatically alter or even end life as we know it. Asteroids, like the one that wiped out the dinosaurs 66 million years ago, are just one example. Space agencies like NASA and ESA have developed programs to track and, if necessary, deflect these objects, but it's a race against time as we discover more of them every year. Some asteroids are massive enough that if they collided with Earth, they could cause global devastation, triggering climate changes that could lead to mass extinction events. Solar storms present another danger. The sun's eruptions of solar energy and plasma, known as coronal mass ejections, CMEs, have the potential to disrupt Earth's magnetic field. This can cause widespread damage to electrical grids, disable satellites, and knock out communication networks. The most severe solar storm on record, the Carrington event of 1859, was powerful enough to set telegraph systems on fire and produce auroras visible as far south as the Caribbean. If a similar event were to occur today, the impact on our technologically dependent world could be catastrophic. Yet, despite the risks, space also offers hope and opportunity. In the past few decades, the idea of colonizing other planets has gone from science fiction to a tangible goal. Mars, with its similar day length and the presence of frozen water, has become the prime candidate for a human colony. NASA, SpaceX, and other space agencies are actively planning missions to establish a human presence on Mars. The dream of becoming a multi-planetary species is no longer just a fantasy. It's a necessity if humanity wishes to secure its survival against cosmic and environmental threats. Elon Musk's SpaceX is leading the charge with the Starship program, aiming to create a reusable spacecraft capable of ferrying large numbers of people to Mars. The challenges are enormous: radiation exposure, lack of atmosphere, and the psychological toll of isolation, to name a few. But the benefits of establishing a presence beyond Earth are equally great. A Mars colony could act as a backup for humanity, ensuring that even if Earth becomes uninhabitable, human civilization can continue elsewhere. Mars isn't the only option for colonization, though. Some scientists propose building habitats on the Moon as a stepping stone for deeper space missions. The Moon's proximity makes it an ideal testing ground for developing the technology needed for life on other planets. In addition, it could serve as a base for mining resources or producing rocket fuel, using the Moon's abundant ice deposits. The Artemis program, led by NASA, aims to return humans to the Moon in the coming years, with plans to establish a sustainable presence by building a lunar base. Beyond the Moon and Mars, the outer planet's moons present even more fascinating possibilities. Europa, one of Jupiter's moons, has a subsurface ocean beneath its icy crust. If liquid water exists, so might life in forms we have yet to imagine. Titan, Saturn's largest moon, is another interesting candidate. It has lakes of liquid methane and ethane, and while this environment is unlike anything on Earth, it suggests that life could develop in conditions we currently find inhospitable. Terraforming, the process of transforming a planet's environment to make it habitable for humans, has also been a major focus of research and speculation. Mars, with its carbon dioxide-rich atmosphere, could potentially be terraformed using technology to release greenhouse gases and warm the planet, making it more Earth-like. This process would take centuries, if not millennia, and is fraught with scientific and ethical challenges. However, the allure of turning a barren planet into a thriving ecosystem remains a powerful vision for the future. The vastness of space also offers nearly limitless resources. Asteroids are thought to contain precious metals like platinum and gold, as well as rare minerals that are essential for technology. Companies are already in the planning stages for asteroid mining missions, aiming to extract these resources and bring them back to Earth. The development of such technology could revolutionize industries and reduce the environmental impact of mining on our planet. But it also raises questions about space law and ownership. Who has the right to claim these resources? Space tourism, once the realm of the ultra-wealthy, is also becoming more accessible. Companies like Blue Origin and Virgin Galactic have already launched private missions with civilian passengers. These early flights are just the beginning of what could become a booming industry in the coming decades, with plans for orbital hotels and lunar visits. The experience of seeing Earth from space, known as the overview effect, has been described as life-changing, a profound reminder of our planet's fragility and unity. As more people have the chance to witness this perspective, it could inspire new efforts to protect and preserve Earth's environment. We can't forget the technological marvels that have made these explorations possible. The James Webb Space Telescope, launched as the successor to the Hubble, is set to uncover new details about the universe's earliest galaxies and the formation of stars. With its powerful infrared capabilities, it can peer through the cosmic dust that has obscured our view of the far reaches of space, providing insights into phenomena we've only begun to imagine. It's a tool that may even help us identify signs of life on exoplanets by analyzing their atmospheres for biomarkers like oxygen, methane, and water vapor. One of the most exciting prospects is the development of faster-than-light travel, or at least a way to traverse the vast distances of space more efficiently. Concepts like the Alcubierre warp drive, inspired by Einstein's theories, suggest that bending space-time itself could allow a spacecraft to move faster than light by shrinking space in front of it and expanding it behind. While this remains theoretical and would require vast amounts of energy, it shows that even the laws of physics, as we understand them, might not be insurmountable obstacles. Meanwhile, the pursuit of a unified theory of everything continues. Physicists are working to bridge the gap between quantum mechanics and general relativity, hoping to unlock a deeper understanding of how the universe operates at both the largest and smallest scales. Discoveries in this field could revolutionize technology, perhaps even leading to the control of gravity or the harnessing of energy from space itself. Such breakthroughs might be key to building the advanced propulsion systems needed for interstellar travel. In this vast cosmic theater, Earth remains a fragile and unique home, teetering on the edge of countless possibilities. As we push further into space, we are reminded of the importance of preserving our planet and ensuring that future generations can gaze up at the stars and dream of exploration, just as we do now. The story of space is far from over. In fact, we are just at the beginning of an epic journey that will reshape our understanding of life, the universe, and our place within it. The discoveries we make will not only satisfy our curiosity, but may determine the fate of humanity itself. The cosmos, with its seemingly infinite expanse, continues to present us with mysteries that challenge our understanding of reality itself. One such mystery is the existence of parallel universes. The multiverse theory, which suggests that our universe might be just one of many, is gaining traction among physicists. According to this theory, an infinite number of universes may exist, each with its own set of physical laws and constants. In some, life as we know it could be impossible. In others, it might flourish under entirely different conditions. These alternate realities might explain why the conditions in our universe are so precisely tuned for life. Perhaps it's just one of countless universes where life is possible. The notion of parallel universes also ties into the study of black holes and the concept of the event horizon, the point beyond which nothing, not even light, can escape. Some physicists speculate that black holes could be gateways to other universes. When a star collapses and forms a black hole, the matter that falls into it might not be destroyed, but instead pass through to another realm. This is purely theoretical, of course, as anything that crosses an event horizon is lost to us forever. However, the idea that black holes might be portals or even the birthplaces of new universes opens up a fascinating realm of possibilities for understanding the fundamental nature of existence. Moving from the theoretical to the observational, dark matter remains one of the most perplexing puzzles in astrophysics. Though it doesn't emit, absorb, or reflect light, dark matter is believed to make up about 27% of the universe. Its presence is inferred from the gravitational effects it exerts on visible matter, such as galaxies and galaxy clusters. Without dark matter, the structures we observe in the universe would not hold together. Researchers have tried for decades to detect dark matter particles directly, building underground detectors and launching experiments in space. But so far, its true nature remains elusive. Understanding dark matter could reveal not only what it is, but also how galaxies form and evolve over billions of years. Linked closely with dark matter is the concept of dark energy, an even more mysterious force. Dark energy is thought to be responsible for the accelerated expansion of the universe. In the late 1990s, scientists observed that galaxies were not just moving apart, but were doing so at an ever-increasing rate. This discovery was groundbreaking, as it suggested that a previously unknown energy was pushing galaxies away from each other, working against the force of gravity. Today, dark energy is estimated to make up about 68% of the universe, yet we know almost nothing about its properties. Its discovery has led scientists to question whether our understanding of gravity is incomplete and whether the universe's ultimate fate will be a big rip, where everything, from galaxies to atoms, is torn apart. As we try to unlock the secrets of dark matter and dark energy, technological advancements are paving the way for new discoveries. The Large Hadron Collider, LHC, the world's most powerful particle accelerator, continues to probe the fundamental particles that make up the universe. By smashing protons together at near-light speeds, the LHC recreates conditions similar to those moments after the Big Bang, allowing scientists to study the building blocks of matter. In 2012, the discovery of the Higgs boson at the LHC was a monumental step forward, confirming the mechanism that gives particles mass. Yet, the LHC has also revealed anomalies that suggest new physics might be at play, possibly hinting at connections between dark matter and the fundamental forces of the universe. Beyond particle physics, the exploration of our solar system's outer reaches has brought its own set of surprises. The Voyager 1 and 2 probes, launched in 1977, have now traveled beyond the heliosphere, the bubble of solar wind surrounding our solar system, and entered interstellar space. These spacecraft, carrying the famous golden records intended to communicate with any intelligent life they might encounter, continue to send back data from regions of space never before explored by humanity. Their discoveries of cosmic rays, magnetic fields, and plasma waves beyond our solar system provide a unique glimpse into the environment between stars. Meanwhile, the mysteries of our own solar system continue to captivate scientists. Jupiter's Great Red Spot, a storm larger than Earth that has raged for centuries, shows signs of shrinking, and researchers are studying why this iconic feature might be disappearing. Saturn's rings, among the most beautiful sights in our solar system, are slowly fading as the planet's gravity pulls them inward. It's estimated that in another 100 million years, the rings might disappear entirely, leaving Saturn a more barren sight than we know today. Even our Sun, a seemingly constant source of energy, is subject to change. It's currently in the middle of its life cycle, but eventually, it will evolve into a red giant, expanding to such an extent that it could engulf the inner planets, including Earth. This process, billions of years away, will transform the solar system, turning what is now a vibrant hub of life into a harsh, inhospitable environment. However, before that happens, humanity might have already expanded its reach beyond the solar system, ensuring the survival of our species. The potential for human expansion into the cosmos hinges on developing advanced propulsion systems. One of the most promising concepts is ion propulsion, which uses electric fields to accelerate ions and create thrust. This technology, already tested in missions like NASA's Dawn spacecraft, is efficient and could make long-distance travel within our solar system more feasible. For interstellar travel, however, more radical ideas are being explored, such as fusion propulsion and light sails. Fusion engines would harness the same reaction that powers the sun, providing massive energy output, while light sails would use the pressure of photons from a laser or the sun to propel spacecraft at incredible speeds. These concepts, while still theoretical, are actively being researched as humanity looks beyond our solar neighborhood. And what of communication with other civilizations, if they do exist? The technology we use today, based on radio waves, may be insufficient for detecting or interpreting alien signals. Advanced civilizations might communicate through means that we have yet to develop, such as laser communication or even quantum entanglement, which would allow for instantaneous communication across vast distances. The study of fast radio bursts, FRBs, mysterious signals from deep space, has intrigued scientists. These bursts are extremely short but powerful, and while most likely natural in origin, they have sparked speculation about the possibility of alien technology at work. In the search for alien life, Earth analogs or exoplanets that resemble Earth are among the most exciting targets. With missions like the Kepler Space Telescope and the upcoming James Webb Space Telescope, astronomers have identified several exoplanets within their star's habitable zones. Proxima Centauri b, for example, orbits the closest star to our solar system and lies within the zone where liquid water could exist. Other planets like TRAPPIST-1e are part of multi-planet systems that show promise for habitability. Studying these worlds may one day provide definitive proof of life beyond Earth, or even offer new homes for humanity in the distant future. Life, if it exists elsewhere, may not resemble anything we know. On Earth, extremophiles thrive in conditions once thought impossible, such as boiling hot springs, acidic lakes, or deep-sea vents. These discoveries expand the possibilities of where life might exist in space. The icy moons of Jupiter and Saturn, like Europa and Enceladus, have oceans beneath their crusts that might harbor life. In the coming years, missions are planned to drill into these icy surfaces and explore the subsurface oceans, searching for signs of microbial life. As we peer deeper into space, our understanding of the universe's origins continues to evolve. The Big Bang Theory, while widely accepted, still has gaps that scientists are eager to fill. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a map of the early universe. However, anomalies within this radiation suggest there may be elements of the universe's formation that we don't yet understand. Alternative theories, like the idea of a cyclical universe where expansion and contraction repeat endlessly, challenge the traditional model and push the boundaries of cosmology. The more we learn, the more questions arise, proving that space is an ever-expanding frontier of wonder and discovery. The answers may lie just beyond our reach, but as our technology advances, humanity stands on the brink of revelations that could change everything we know about our universe and ourselves. As humanity continues to push the boundaries of exploration, one of the most exciting developments is the rise of autonomous space exploration technology. With the vast distances and inhospitable conditions of space, sending human astronauts to every corner of our solar system, or beyond, is not always feasible. Instead, robotic explorers, drones, and AI-driven systems are taking the lead. These machines are designed to withstand the harsh environments of space, and they provide the opportunity to explore regions that are too dangerous or distant for humans. Mars, for instance, has become a hub of robotic exploration. NASA's Perseverance rover, which landed on the Martian surface in 2021, is not only collecting rock samples, but is also accompanied by a small helicopter, Ingenuity, which has been conducting aerial reconnaissance missions. This marks the first time a powered flight has been performed on another planet, setting the stage for future drones that could explore the skies of distant worlds like Titan, Saturn's moon. These robotic explorers are equipped with AI to make autonomous decisions, avoiding obstacles and identifying points of interest without waiting for commands from Earth. Looking beyond Mars, the exploration of asteroids is also advancing rapidly. NASA's OSIRIS-RX mission recently completed its mission to collect samples from the asteroid Bennu, a near-Earth object that could contain clues about the early solar system. This type of mission is not only a scientific endeavor, but also a test run for potential future mining operations. Asteroids are rich in valuable minerals and metals, including rare earth elements critical for technology production. The successful retrieval of these resources could revolutionize industries on Earth, creating new economic opportunities and reducing the environmental impact of mining. The exploration of the outer solar system has brought with it some of the most surprising discoveries. The Cassini mission, which orbited Saturn for 13 years, revealed that its moon Enceladus has geysers of water vapor erupting from its surface. These plumes are evidence of a subsurface ocean, which could potentially harbor life. Cassini's findings were so intriguing that future missions are now being planned to dive through these plumes and analyze the water for signs of microbial life. Similarly, the Juno mission has been studying Jupiter's massive storms and magnetic fields, offering insights into the dynamics of gas giants, which are fundamentally different from the rocky planets we are more familiar with. Closer to home, the study of the Earth's own atmosphere and its interaction with space is a field gaining attention. The Earth's magnetic field, a protective barrier against solar and cosmic radiation, is not as stable as it might seem. Over geological timescales, the magnetic poles have flipped, with the last reversal occurring roughly 780,000 years ago. Scientists are now studying whether another such flip might be imminent, as the magnetic field has been weakening over the past few centuries. If this happens, it could temporarily leave the planet more exposed to solar radiation, with implications for satellite technology and even climate patterns. The concept of space weather, events like solar flares and cosmic ray bursts, also highlights the vulnerability of our technological infrastructure. Space agencies around the world are working to develop early warning systems for solar storms. These storms can damage satellites, disrupt power grids, and affect communication systems. The 1989 geomagnetic storm, for instance, knocked out power in parts of Canada for hours. As our reliance on satellite technology grows, understanding and preparing for space weather becomes increasingly critical to protecting modern civilization. Another key area of research is the study of gravitational waves, ripples in the fabric of space-time caused by the acceleration of massive objects like merging black holes or neutron stars. The detection of gravitational waves in 2015 by the LIGO Observatory marked a new era in astronomy. Unlike light, which can be blocked by cosmic dust, gravitational waves pass through everything, offering a completely new way to observe the universe. They allow scientists to study cosmic events billions of light years away, events that would otherwise remain invisible. Future observatories, such as the space-based LISA mission, will be able to detect even fainter and more distant waves, potentially uncovering new insights into the nature of black holes and the origins of the universe. One of the most ambitious projects currently in development is the concept of building a space elevator. This idea, which once belonged to the realm of science fiction, involves creating a tether that extends from Earth's surface into space, anchored by a satellite or space station. Such a structure would revolutionize space travel, providing a cost-effective and efficient way to transport materials and people into orbit without the need for rockets. The biggest challenge is finding a material strong enough to withstand the immense forces involved. Current research focuses on carbon nanotubes and other advanced composites that could one day make the space elevator a reality. With all the technological advancements being made, the ethical questions surrounding space exploration are becoming more prominent. For instance, as we search for life beyond Earth, we must also consider the potential consequences of contamination. Space agencies are developing strict protocols to prevent Earth organisms from hitching a ride on spacecraft and contaminating other worlds. The reverse is also a concern. If we bring back samples from Mars or other planets, there's the risk of introducing unknown pathogens or organisms to Earth's ecosystem. Planetary protection measures are thus a top priority in planning future missions. Another ethical debate revolves around the ownership and commercialization of space. With private companies like SpaceX and Blue Origin rapidly expanding their capabilities, the prospect of mining asteroids and building lunar bases is becoming more tangible. However, international laws like the Outer Space Treaty, signed in 1967, state that no nation can claim ownership of the moon or other celestial bodies. This leaves a gray area for private companies and raises questions about how resources will be managed and who will have access to the benefits they bring. Space colonization, while promising, also brings with it discussions about inequality and accessibility. If Mars colonization becomes a reality, who gets to go? Will it only be available to the wealthy, or will there be efforts to make space accessible to all? The costs involved in building habitats, transporting people, and maintaining life support systems are enormous, and ensuring that space remains a realm of exploration and not exploitation is a challenge that humanity must face as we expand our reach. As we contemplate sending humans deeper into space, the question of how our bodies will adapt remains crucial. Astronauts aboard the International Space Station, ISS, experience the effects of microgravity, including muscle atrophy, bone density loss, and vision problems. Long-term missions to Mars or beyond would expose astronauts to these conditions for much longer periods, not to mention the increased radiation levels outside Earth's protective atmosphere. Scientists are studying ways to mitigate these risks, such as developing artificial gravity habitats and radiation shielding. Solving these challenges will be key to ensuring the health and safety of astronauts as they venture further from Earth. The dream of finding life beyond our planet remains one of the driving forces behind our quest into the cosmos. The study of extremophiles on Earth has revealed that life can thrive in conditions far more extreme than previously imagined, such as in the deep ocean hydrothermal vents, under the ice of Antarctica, or within acidic hot springs. These discoveries increase the likelihood that life, in some form, could exist elsewhere in our solar system or beyond. Missions are being designed to search for biosignatures, evidence of life such as organic molecules or specific gases like methane, in the atmospheres of exoplanets. The James Webb Space Telescope will play a crucial role in this search, analyzing the chemical composition of distant planets' atmospheres. In the vastness of space, one of the most profound discoveries may not be finding life, but realizing the interconnectedness of the universe itself. Quantum entanglement, a phenomenon where particles remain connected even across vast distances, challenges our understanding of space and time. It suggests that everything in the universe is linked at a fundamental level. Some theorists propose that this quantum connection could be harnessed for communication, leading to faster-than-light information transfer. While still speculative, this could revolutionize how we explore and interact with the cosmos. The universe is not just an external realm to be explored. It is deeply intertwined with our existence. From the atoms that form our bodies, forged in the hearts of stars, to the forces that bind galaxies, we are a part of the cosmos, both observers and participants. As our knowledge expands, so too does our awareness of how fragile our position in the universe is. The vast distances, the cosmic forces, and the unknown variables remind us that, despite all our technology and knowledge, there is still much beyond our control. Humanity's journey into space is not just a pursuit of knowledge. It is a quest for survival, a need to ensure that our species continues beyond the confines of Earth. The answers we seek among the stars may redefine our understanding of life and reshape our civilization. Each discovery, whether it is an alien microbe beneath the ice of a distant moon or the confirmation of a parallel universe, will push the boundaries of science and philosophy alike. As we stand at the edge of this new frontier, the future of space exploration holds infinite possibilities. Whether we find new worlds to inhabit, uncover the secrets of dark matter, or make contact with another civilization, the journey will undoubtedly transform humanity, leading us to a deeper understanding of our place in the grand tapestry of the universe. The story of space exploration is as much about human ingenuity and curiosity as it is about the vast unknown stretching out before us. With each passing year, our technology evolves, allowing us to look further, understand more, and even manipulate the environment of space itself. But as our capabilities expand, so too does the complexity of the questions we face, particularly as we start to interact more directly with celestial bodies. One of the most ambitious and forward-thinking concepts in this regard is terraforming. The idea of transforming another planet's environment to make it habitable for human life. Mars is at the forefront of these discussions, but the reality of altering an entire planet's atmosphere and ecosystem is daunting. To terraform Mars, scientists propose increasing the planet's temperature and thickening its atmosphere, possibly by releasing greenhouse gases stored in the soil or by building massive orbital mirrors to reflect sunlight onto the surface. This would potentially allow liquid water to flow and create conditions suitable for plant life. However, the challenges are enormous. Mars has a thin atmosphere composed mostly of carbon dioxide, and it lacks a magnetic field, which means that any atmosphere created could be stripped away by solar winds over time. Even if we manage to warm Mars and introduce water, the lack of a protective magnetic shield could make it impossible to sustain a breathable atmosphere for long. The ethics of terraforming are another concern. Mars, though barren, is still a natural part of the universe with its own geological history. Altering it for human use raises questions about the rights of planets and the potential to disrupt any existing ecosystems we may not yet have discovered. If microbial life exists on Mars, terraforming could destroy it before we even have a chance to study it. Some argue that humanity should focus on adapting to environments as they are, rather than forcing them to conform to our needs. This debate will likely intensify as technology progresses and the possibility of Mars colonization becomes more feasible. While Mars remains a target for human colonization, some researchers are exploring the idea of building habitats in the void of space itself. Space stations like the International Space Station, ISS, serve as the first step in this direction, demonstrating how humans can live and work in low Earth orbit for extended periods. However, the ISS is still dependent on Earth for supplies, and the effects of long-term microgravity on the human body, such as bone density loss and muscle atrophy, present ongoing challenges. For humanity to establish truly independent colonies in space, more advanced life support systems and solutions to artificial gravity must be developed. One concept gaining traction is the creation of rotating space habitats, sometimes referred to as O'Neill cylinders, which simulate gravity through centrifugal force. These massive structures could support human life by creating Earth-like environments in space, complete with artificial weather systems, agriculture, and ecosystems. Building such habitats would be a monumental engineering feat, requiring materials and technologies that are still in their infancy. However, these structures could serve as stepping stones for deeper space missions, providing safe havens for humans on their journey beyond our solar system. Space stations aren't just about colonization. They also play a crucial role in advancing scientific research. Experiments conducted in microgravity on the ISS, for example, have led to breakthroughs in materials science, biology, and medicine. In zero-gravity conditions, scientists can grow protein crystals and study cell behavior in ways that are impossible on Earth. These discoveries have implications for drug development and medical treatments, showing that space exploration benefits not just our understanding of the cosmos, but also life on Earth. As the dream of human space colonies inches closer to reality, we must also consider the psychological effects of space travel. Living in confined spaces with limited social interaction and the vast emptiness of space outside can take a toll on mental health. Isolation, confinement, and the sensory monotony of space have been studied extensively by space agencies. Techniques to combat these effects include virtual reality systems that simulate natural environments, as well as carefully designed exercise routines and social activities to maintain physical and mental well-being. The ability to adapt to these psychological challenges will be critical for long-duration missions, such as a journey to Mars, which could take years to complete. Beyond the physical and mental hurdles, the idea of sending humans into deep space raises the question of biological adaptation. In space, cosmic radiation poses a significant risk to human health, with high-energy particles that can penetrate spacecraft and human tissue. Long-term exposure increases the risk of cancer and can damage the central nervous system, leading to cognitive decline. To mitigate these risks, scientists are exploring ways to shield astronauts using advanced materials or even leveraging the spacecraft's own water supply as a radiation buffer. Genetic engineering is also being considered as a future solution, potentially creating space-adapted humans who are more resistant to radiation and other hazards. As we move beyond the confines of our solar system, the quest for finding Earth-like planets becomes more critical. The Kepler Space Telescope, followed by the James Webb Space Telescope, has identified thousands of exoplanets, some of which reside in the habitable zone of their stars, where conditions could allow for liquid water. However, not all habitable zones are created equal. The type of star a planet orbits plays a huge role in its potential for life. For example, red dwarf stars are common in the galaxy and have planets in their habitable zones. But these stars are prone to violent solar flares that could strip away a planet's atmosphere or make its surface inhospitable. Studying these planets further will help us understand where life might thrive or struggle in the cosmos. One of the most promising systems discovered is TRAPPIST-1, which hosts 7 rocky planets, 3 of which are in the habitable zone. These planets are similar in size to Earth and may have the right conditions for liquid water. In the coming years, the James Webb Space Telescope will analyze the atmospheres of these planets for signs of water vapor, oxygen, and other markers that could indicate the presence of life. The study of exoplanets is evolving rapidly, and it is possible that within the next decade, we may identify worlds that are not only habitable, but inhabited. Meanwhile, the search for life also continues within our own solar system. Missions are being planned to explore Europa, one of Jupiter's moons, which is believed to have a vast ocean beneath its icy crust. A robotic probe could one day land on Europa, drill through the ice, and send a submersible into the ocean below to search for signs of life. Such missions present enormous technical challenges, but the potential discovery of even microbial life would be one of the greatest scientific achievements of all time. In addition to Europa, Saturn's moon Titan is another target of interest. Titan has lakes and rivers of liquid methane and ethane, a completely different kind of environment than anything found on Earth. The Dragonfly mission, set to launch in the 2030s, aims to explore Titan's surface using a rotorcraft drone, which will fly from site to site in search of complex organic compounds. The findings could reveal whether life can exist in environments vastly different from the water-based ecosystems on Earth, broadening our understanding of life's adaptability. While the search for life and habitable planets continues, the broader question of humanity's place in the universe remains. The exploration of space is not just a technological or scientific endeavor. It is also a philosophical and existential one. The possibility that intelligent civilizations might exist somewhere in the cosmos raises profound questions about our origins, our future, and the nature of consciousness. If we do eventually make contact with an alien civilization, how will it impact our societies, religions, and philosophies? Will it unite humanity under a common cause, or create divisions based on fear and uncertainty? Some researchers argue that before we actively try to contact other civilizations, we should carefully consider the risks. The history of human exploration on Earth often involved conflicts between cultures, and there is no guarantee that a technologically advanced civilization would be benevolent. This has led to debates about the protocols of messaging extraterrestrial intelligence, METI. While SETI focuses on listening for signals, METI involves sending messages into space with the hope of establishing contact. The ethical and practical implications of these efforts are hotly debated among scientists and ethicists alike. Regardless of the outcome, the pursuit of knowledge and the drive to explore are fundamental aspects of the human spirit. Space exploration is about more than finding new worlds. It is about expanding the boundaries of what it means to be human. Whether we find other civilizations or face the silence of an empty cosmos, the journey will push our species to evolve and adapt, challenging us to reach heights we once thought impossible. As we look to the stars, we are not just searching for other forms of life. We are seeking a deeper understanding of ourselves and our place in the grand universe. The future of space is filled with promise and peril. Each step we take, each mission we launch, opens up a new chapter in the story of humanity, one that may span beyond the confines of Earth and continue for millennia. Whether it's establishing colonies, mining asteroids, or communicating with alien civilizations, the decisions we make today will shape the destiny of our species. In the end, our journey through space may be the greatest adventure humanity has ever embarked upon, a story of discovery, adaptation, and the quest for meaning in the vast, uncharted territories of the cosmos. As humanity's gaze remains fixed on the stars, the possibilities for our future in space seem endless. Yet each step into the cosmos brings both technological marvels and new questions about survival, sustainability, and our fundamental nature. While much of the focus today centers on Mars missions and lunar bases, another revolutionary idea gaining momentum is the construction of space habitats that could orbit planets, asteroids, or even exist independently in deep space. These habitats are more than just futuristic concepts. They represent a vision where human civilization could expand beyond Earth's confines, creating self-sustaining ecosystems among the stars. One of the most promising designs for these habitats is the concept of the Stanford Torus, a massive, rotating ring that would simulate Earth-like gravity through centrifugal force. By rotating at a specific speed, the habitat would create artificial gravity, allowing humans to walk and live much as they do on Earth. Such a structure would include residential areas, agriculture zones, and green spaces, all encapsulated in a protective shell to shield inhabitants from cosmic radiation. The goal is to make life in space as comfortable and sustainable as possible, transforming these habitats into cities where people could thrive for generations. Building these habitats would require immense resources, far beyond what is currently feasible to launch from Earth. This is where asteroid mining and the utilization of in-situ resources come into play. Asteroids contain not only valuable metals like platinum and nickel, but also water, which can be split into hydrogen and oxygen for rocket fuel or used to sustain life. By mining these asteroids, space habitats could be built and maintained with resources already available in space, dramatically reducing the need to transport materials from Earth. This would make the construction of large-scale habitats and space stations more economically viable and sustainable. The Moon also plays a crucial role in the development of space infrastructure. Lunar regolith, the dusty surface material of the Moon, is rich in oxygen and metals that can be used for construction. Plans are already in motion for the creation of lunar bases that would serve as hubs for mining operations, scientific research, and as a stepping stone for missions deeper into the solar system. The European Space Agency, ESA, and NASA have proposed building a lunar gateway, an orbiting space station around the Moon that would support these operations and act as a waypoint for future Mars missions. Such infrastructure is essential not just for exploration, but for establishing a permanent human presence beyond Earth. As we explore these new frontiers, the importance of sustainable life support systems becomes increasingly clear. Plants are at the center of many of these designs, as they provide oxygen, absorb carbon dioxide, and can produce food. Advanced hydroponic and aeroponic systems are being developed to grow crops in space, using minimal water and no soil. The success of these systems will be critical in creating closed-loop ecosystems, where everything, from waste recycling to food production, is carefully managed to minimize resource consumption and ensure that life can flourish in isolated environments far from Earth. Food production, however, is just one aspect of sustainable living in space. Water, one of the most critical resources, will need to be recycled almost entirely. The International Space Station, ISS, has already implemented water reclamation systems that purify and reuse almost every drop of water, including moisture from the air and urine. These systems will be scaled up and refined for use in future habitats, ensuring that water remains abundant even on long-duration missions or permanent settlements. Energy production in space is another essential consideration. Solar power is the most obvious and abundant source of energy available, especially in environments where sunlight is constant and unimpeded by an atmosphere. Future habitats could be equipped with massive solar arrays to harness this energy, providing electricity for all life support systems and technology. In more distant or shadowed environments, nuclear fusion reactors might become a necessity, offering a compact and powerful energy source that could sustain life for extended periods. Research into these technologies is ongoing, and breakthroughs in this area could revolutionize not only space habitats, but energy production on Earth as well. The evolution of space habitats also raises the fascinating possibility of creating entirely new ecosystems, tailored to thrive in the unique environments of space. Genetic engineering could play a significant role in this, allowing scientists to modify plants and even microorganisms to withstand the conditions of low gravity, high radiation, or extreme temperatures. For instance, bacteria could be engineered to break down and recycle waste efficiently, while plants might be designed to grow with less light and water, maximizing productivity and resilience. These bioengineered solutions could make future space habitats more self-sufficient and adaptable, ensuring that life can survive and prosper even in the most inhospitable corners of space. As technology progresses, the concept of building not just habitats but entire cities in space begins to emerge. These orbital megastructures could host thousands or even millions of people, functioning as hubs for trade, research, and culture. Imagine a city orbiting Mars, where scientists, engineers, and artists collaborate, creating a vibrant society far from Earth. Such cities would not only support planetary exploration, but could become centers of learning and development, pushing the boundaries of human culture and civilization. These visions of space cities also bring us closer to the idea of interplanetary trade. Resources mined from asteroids and planets could be transported between Earth, Mars, and other colonies, creating an economy that extends beyond our home planet. Rare metals and minerals needed for advanced technologies might be sourced from distant asteroids, while food and materials could be exchanged between lunar bases and Martian settlements. An interplanetary economy would transform humanity's relationship with space, making it a true extension of Earth's ecosystem and economy rather than an isolated venture. Yet, while the prospect of space expansion and development is thrilling, it's not without its risks and challenges. As we begin to colonize and industrialize space, there are growing concerns about environmental impact. Space debris, a byproduct of decades of satellite launches and defunct spacecraft, already poses a significant threat to both manned and unmanned missions. Collisions between debris fragments can create cascading events, known as the Kessler syndrome, where space becomes increasingly cluttered and dangerous for further exploration. Mitigating this risk requires new technologies for debris capture and management, ensuring that space remains safe for future missions and habitats. Additionally, the issue of planetary protection becomes even more pressing as humanity expands into space. The potential for contaminating other worlds with Earth-based organisms is a significant concern, especially in places like Mars or Europa, where the search for life is a primary objective. Introducing Earth microbes could not only threaten potential alien ecosystems, but also skew scientific research, making it difficult to determine whether life discovered is indigenous or a result of contamination. Strict sterilization protocols and containment measures will be essential to protect both extraterrestrial environments and our own. The ethical implications of space colonization extend beyond contamination. As we establish permanent human presence on other worlds, questions of governance, rights, and culture emerge. How will these new societies be governed? Will they be extensions of Earth's nations? Or will they form independent governments with new laws adapted to life in space? The complexities of creating a fair and equitable society in such extreme conditions will test our political and social systems. Moreover, as space becomes increasingly accessible, there is the risk that only the wealthiest will have the opportunity to live and work in these new environments, perpetuating inequality beyond Earth's boundaries. Despite these challenges, the pursuit of space colonization offers an incredible opportunity for humanity to redefine itself. The technological and ethical obstacles we face may push us to innovate, not just in engineering and science, but in the way we organize societies and distribute resources. The potential of becoming a multiplanetary species could unite humanity under a common goal, fostering a sense of global collaboration that transcends national borders. As our presence in space grows, so too will our understanding of the universe. The next generation of telescopes and probes, such as the James Webb Space Telescope and missions to explore the outer solar system, will continue to expand our knowledge of exoplanets, star formation, and the evolution of galaxies. These discoveries might reveal habitable worlds light years away or uncover phenomena that challenge our understanding of physics and reality itself. Each new piece of data brings us closer to answering the ultimate questions about life, the universe, and our place within it. The journey into space is not just about survival or expansion. It's about exploring the unknown and pushing the boundaries of what is possible. Whether we find alien life, build cities in orbit, or discover new realms of physics, the future of space exploration is one of endless discovery and innovation. Humanity's story is, and always has been, one of exploration and curiosity. As we continue this journey, the cosmos awaits, filled with wonders and challenges that will shape the next chapters of our civilization and transform our understanding of existence itself. As humanity's march into space accelerates, the realization that we may soon become an interplanetary species is both exhilarating and daunting. The challenges we face in this endeavor are immense, yet so are the rewards. Our solar system, and the universe beyond it, is a vast playground of possibilities, some within reach, others that will take generations of innovation and courage to achieve. This vision isn't merely about technological achievement. It's about survival, evolution, and the future identity of humanity. As we continue to step beyond our earthly boundaries, we must also confront the realities of living and thriving in space, including biological, social, and philosophical adaptations. One of the most immediate and pressing concerns is the long-term health effects of space travel. Our bodies evolved under Earth's gravity, and prolonged exposure to microgravity has significant consequences. Astronauts experience muscle atrophy, bone density loss, and fluid shifts that can lead to vision problems and other health issues. For missions to Mars or beyond, these problems are compounded. Researchers are exploring ways to mitigate these effects, such as using artificial gravity through rotating habitats or exercise regimens designed to stimulate muscle and bone growth. However, these solutions are only partial. The long-term consequences of living in reduced gravity, like on Mars, which is only 38% of Earth's gravity, remain uncertain. Developing methods to adapt human physiology to these environments will be crucial for sustainable habitation. Radiation is another formidable challenge. Outside Earth's magnetic field, astronauts are exposed to cosmic rays and solar radiation that can increase cancer risk, damage DNA, and cause neurological issues. On Mars, the thin atmosphere offers little protection. Building habitats underground or using advanced materials to shield against radiation are possible solutions, but they require significant resources and engineering expertise. Some scientists are even exploring genetic modifications as a way to make humans more resistant to radiation, though such interventions raise ethical and safety concerns. The path forward may involve a combination of shielding, medical advances, and new technologies that we have yet to fully develop. As we prepare for life on Mars and other planets, the concept of space agriculture becomes increasingly important. Growing food in space is essential for long-term missions, reducing the reliance on Earth-based supplies. Experiments on the ISS have shown that it's possible to grow crops like lettuce and radishes in microgravity, but expanding this to a self-sustaining agricultural system on another planet will require overcoming significant challenges. Mars, for example, has soil rich in toxic perchlorates, which must be removed or neutralized before it can support crops. Developing soil treatments or hydroponic systems that work in these conditions will be vital. Beyond technological innovation, the social and psychological aspects of living in space present another layer of complexity. Space habitats and future colonies will be confined environments where the stress of isolation, confinement, and the constant awareness of the hostile environment outside can take a toll on mental health. Long-term missions to Mars, which could isolate astronauts for up to 3 years, necessitate new approaches to support their psychological well-being. Virtual reality environments simulating Earth's natural landscapes are being developed to provide mental relief, while carefully structured daily routines and social interaction protocols are being tested to mitigate the effects of prolonged isolation. The future Mars colonies or space habitats will need to develop entirely new societal norms and governance structures. It is likely that these new communities will start as extensions of Earth-based nations or corporations, but over time, they may evolve into independent entities with their own legal systems and cultures. This raises questions about the rights and responsibilities of these future citizens. What kind of laws will govern them? How will resources be distributed fairly in such a remote and isolated environment? The framework for space law is still in its infancy, and international cooperation will be crucial to establish norms that prevent conflict and ensure that space remains a domain for peaceful and equitable exploration. As we consider building self-sustaining colonies on Mars or other planets, the concept of a space economy comes into play. Establishing industries in space will be essential for long-term human habitation. Mining operations on the Moon, for example, could provide helium-3, a potential fuel for nuclear fusion reactors, while Mars could offer access to iron and other essential metals. In-space manufacturing, such as 3D printing using locally sourced materials, will reduce the need to transport heavy equipment from Earth. Companies like SpaceX and Blue Origin are pioneering this new frontier, but as private enterprise increasingly drives space expansion, questions of ownership, regulation, and profit distribution become crucial. Will space be a free market, or will it require international oversight to ensure fair practices? These developments also open the door for an entirely new form of civilization, one that transcends Earth's boundaries and begins to establish a presence across the solar system. This expansion could lead to a variety of human societies developing in parallel, each shaped by the environments in which they reside. Mars might develop a culture deeply attuned to survival and resource management, while lunar colonies could become hubs of research and technology due to their proximity to Earth. Asteroid miners, meanwhile, might form a transient, nomadic society, moving from one resource-rich target to another. This diversification of human experience could lead to a new age of cultural and social evolution, as the conditions of life in space shape these communities in ways we can only begin to imagine. While much of the focus is on Mars and the Moon, the gas giants and their moons present tantalizing possibilities for future exploration. Europa, one of Jupiter's moons, has long intrigued scientists because of its subsurface ocean. Missions like NASA's upcoming Europa Clipper aim to explore this moon's icy surface, searching for signs of life in the water beneath. If microbial life is found there, it would not only prove that life can exist in diverse environments, but also suggest that life might be common throughout the universe. Such a discovery would transform biology, forcing us to reconsider the fundamental requirements for life and possibly providing clues about the origins of life on Earth. Saturn's moon Titan offers another fascinating environment. With lakes of liquid methane and ethane, Titan presents an entirely different kind of habitat, one where life, if it exists, will be based on a chemistry unlike anything seen on Earth. Exploring Titan's surface and atmosphere will require specialized technologies, like the Dragonfly mission's drone, designed to fly through its dense atmosphere. Discovering or even detecting the building blocks of life on Titan could significantly expand our understanding of biochemistry and the adaptability of life, opening up the possibility that life exists in far more places than we currently imagine. The search for life is not limited to our solar system. Astronomers are turning their gaze to exoplanets, worlds orbiting other stars. Advances in telescope technology, particularly the James Webb Space Telescope, allow scientists to study the atmospheres of these distant planets, searching for biosignatures like oxygen, water vapor, and methane. Identifying a planet with the right conditions for life, or even direct evidence of life itself, would be one of the most profound discoveries in history, reshaping our view of the universe and our place in it. The discovery of a habitable exoplanet could also spark new technological developments in interstellar travel, as humanity begins to consider the possibility of reaching other stars. The idea of interstellar travel, once confined to the realms of science fiction, is now being taken seriously by scientists and engineers. Concepts such as breakthrough, starshot envision tiny spacecraft propelled by powerful lasers, traveling at a fraction of the speed of light to reach nearby star systems like Alpha Centauri within a human lifetime. While the technical and energy challenges are immense, even incremental progress in these areas could lay the groundwork for humanity's first steps beyond our solar system. Achieving such a feat would not only mark a milestone in human capability, but also set the stage for an era of exploration that extends across the galaxy. The notion of becoming an interstellar civilization invites us to ponder not just the technical challenges, but also the philosophical implications. If humanity spreads beyond Earth, how will we maintain a sense of identity and unity across such vast distances? Will Earth remain the cultural and political center, or will colonies become independent and diverse, forming entirely new civilizations? Moreover, the ethics of interacting with potential alien life, or the consequences of human expansion on other ecosystems, will require careful consideration and likely an entirely new set of guiding principles. The ultimate question remains: what drives humanity to explore space? Is it simply the survival instinct, a desire to ensure that we are not bound to the fate of a single planet? Or is it something deeper, a yearning to explore, to push the boundaries of knowledge and existence? Space is not just an arena for science and technology. It is the next stage of human evolution, a chance to redefine who we are and what we are capable of. As we continue this journey, the challenges we face will test our resilience, creativity, and collaboration. The cosmos is a vast, untamed frontier, and our exploration of it will be the greatest adventure humanity has ever embarked upon, one that will shape the destiny of our species for generations to come. As humanity prepares to embark on its greatest journey yet, transforming from an earthbound species to one that spreads across the cosmos, the challenges, opportunities, and ethical dilemmas we face are becoming increasingly complex. Each step forward brings new discoveries and innovations, but also new questions that test our understanding of what it means to be human. Our future in space is not just about survival. It's about thriving, expanding, and possibly redefining civilization itself. As we move toward the stars, the technologies we develop, the societies we create, and the mysteries we uncover will shape the very fabric of our existence. One of the most critical aspects of deep space exploration is the development of propulsion systems capable of carrying humans to distant destinations in a fraction of the time current technologies allow. Chemical rockets, which have served us well for lunar missions and low Earth orbit travel, are not suitable for long-distance journeys like Mars or beyond. Researchers are exploring advanced propulsion systems such as nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP, both of which promise greater efficiency and speed. NTP uses nuclear reactions to heat a propellant, producing thrust that could significantly reduce travel time to Mars. NEP, on the other hand, converts nuclear energy into electricity to power ion thrusters, which, while slower to accelerate, could operate continuously over long durations, making it ideal for deep space travel. Another revolutionary concept under consideration is the use of fusion propulsion. Fusion, the process that powers the sun, involves fusing atomic nuclei to release vast amounts of energy. If harnessed, fusion engines could propel spacecraft at unprecedented speeds, enabling missions to Mars in weeks rather than months, or even making interstellar travel a possibility. The technical challenges of controlling and sustaining a fusion reaction in the vacuum of space are immense, but recent advances in fusion technology and the development of experimental reactors on Earth provide hope that this could become a reality within the century. The successful deployment of fusion propulsion would not only transform space travel, but could also revolutionize energy production on Earth, providing a clean, virtually limitless power source. For missions extending beyond Mars, such as to the moons of Jupiter and Saturn, or even to the Kuiper Belt, advanced propulsion systems alone won't be enough. These missions will require spacecraft capable of supporting human life for decades, if not longer. This brings us to the concept of generation ships, massive spacecraft designed to carry entire communities of people who live, work, and raise families during the journey. Such ships would need to be entirely self-sufficient, featuring closed-loop life support systems, food production facilities, and sustainable energy sources. The idea of generation ships challenges our conception of society, as those born on these ships may never know Earth as home, instead identifying with their vessel and its mission. The construction of these generation ships will demand advanced space manufacturing capabilities. Asteroid mining, as previously mentioned, will play a crucial role, providing raw materials like metals, water, and other essential resources. The technology for in-space manufacturing is rapidly advancing. 3D printing has already been tested aboard the ISS, demonstrating the potential to produce parts and tools on demand. Scaling this up to manufacture entire spacecraft and habitats in space will reduce the need to launch heavy materials from Earth, making construction more feasible and cost-effective. As these technologies develop, it may become possible to build vast space stations and interplanetary vessels directly in orbit, eliminating the constraints of Earth's gravity and atmosphere. As we move deeper into space, we must also consider the energy requirements for such missions. Solar power, while effective near Earth and Mars, becomes less viable in the outer solar system, where sunlight is much weaker. Here, nuclear power becomes essential, particularly nuclear fission reactors, which could provide a steady energy supply for spacecraft and bases on distant moons. NASA's Kilo Power project is already developing compact nuclear reactors designed to power lunar and Martian habitats. For deeper space missions, larger, more advanced reactors will be necessary, as will systems capable of converting energy efficiently and safely over long periods. In addition to propulsion and energy, life support and habitat technologies must evolve to support long-duration missions. Developing habitats that can maintain Earth-like conditions, complete with temperature control, breathable air, and protection from cosmic radiation, requires innovation. One promising avenue is the development of inflatable habitats, which can be launched in compact forms and expanded once in space. These structures can be outfitted with radiation shielding and temperature regulation systems, and they offer flexibility in design, allowing for modular space stations and bases that can adapt as needs change. The concept of creating artificial gravity through rotation is also being tested in these designs, potentially mitigating the health risks associated with prolonged exposure to microgravity. The expansion into space also brings about the exciting potential for space tourism and commercial development. Companies like SpaceX, Virgin Galactic, and Blue Origin are pioneering private space travel, offering suborbital flights and soon orbital vacations. The rise of space tourism is not just a luxury for the wealthy, it's a crucial step in making space more accessible and affordable. The revenue generated from these early ventures will fund further technological advancements, ultimately lowering the cost of space travel and building the infrastructure needed for future colonies. Private sector involvement in space is likely to drive innovation at a pace faster than ever before, but it also requires new regulatory frameworks to ensure safety, sustainability, and fair access. The commercialization of space extends beyond tourism. The construction of space hotels, lunar mining operations, and orbital manufacturing facilities are all being actively planned. The International Space Station has already hosted private missions, and plans for the development of commercial space stations are underway. These new stations could serve as hubs for research, industry, and tourism, creating a thriving economy in low Earth orbit. The expansion of this economy will set the stage for more ambitious projects, such as building permanent bases on the Moon and Mars, developing large-scale asteroid mining operations, and constructing interplanetary transport networks. As the space economy grows, the legal and ethical questions surrounding ownership and resource exploitation become increasingly significant. The Outer Space Treaty of 1967, which prohibits the appropriation of celestial bodies by any nation, provides a framework for international cooperation, but it was drafted before private companies became major players in space exploration. New treaties and agreements will be needed to ensure that space resources are managed fairly and sustainably, preventing monopolies and conflicts. The development of space law is a delicate balance between encouraging innovation and ensuring that space remains a shared domain for the benefit of all humanity. Beyond the solar system, the discovery of thousands of exoplanets has ignited our imagination about the possibility of finding habitable worlds light years away. As the search for Earth-like planets continues, astronomers are developing techniques to study these distant worlds in detail. Spectroscopy, for example, allows scientists to analyze the light passing through a planet's atmosphere, revealing its composition. The presence of oxygen, water vapor, or methane could indicate that a planet has the conditions necessary for life. The James Webb Space Telescope and other advanced observatories will soon begin scanning these planets for such biosignatures, and the discovery of even microbial life would profoundly change our understanding of biology and our place in the cosmos. The idea of contacting or even visiting these distant worlds presents challenges that go beyond technology. The distances between stars are so vast that even with advanced propulsion systems, interstellar travel would take decades, if not centuries. This has led to the exploration of concepts like warp drives, inspired by Einstein's theory of relativity, which could theoretically allow for faster-than-light travel by bending spacetime itself. While this remains speculative, researchers are exploring how quantum mechanics and our understanding of the fabric of space might one day unlock new modes of travel. Meanwhile, the search for intelligent extraterrestrial civilizations, led by projects like SETI, Search for Extraterrestrial Intelligence, continues. The vast silence of space raises the question: if intelligent life is common, why haven't we detected it? This is the essence of the Fermi paradox. One possibility is that civilizations are avoiding contact for fear of threats, or they communicate using technologies we haven't yet developed. Another theory suggests that intelligent life may be rare, or that civilizations inevitably self-destruct before reaching the point of interstellar communication. Understanding why we haven't yet found evidence of intelligent life, or if we eventually do, will shape the trajectory of human exploration and the future of our species. The philosophical implications of finding life, whether microbial or intelligent, are profound. It would challenge our understanding of existence, potentially revealing that life is not a rare phenomenon, but an integral part of the universe. This discovery could transform human identity, prompting us to redefine our place in the cosmos and our relationship with other life forms. It might inspire a new era of unity on Earth, as humanity recognizes its shared responsibility as caretakers of life in a vast, interconnected universe. As humanity continues its journey into space, the possibilities are endless and the challenges are vast. Each step we take builds upon the last, pushing the boundaries of what is possible and expanding our understanding of the universe. The future will likely be a mix of triumphs and setbacks, but the drive to explore and the spirit of innovation that has defined human progress will propel us forward. The cosmos beckons, full of mysteries and potential, and our journey into its depths will shape the next chapter of human civilization. This new era of exploration promises not only to expand our reach, but to deepen our understanding of life, existence, and the universe itself. As humanity continues its relentless quest to explore and expand into the cosmos, we must confront not only the technological and logistical challenges, but also the cultural, societal, and existential shifts that will inevitably accompany our journey into space. The future of space exploration is not just about sending humans and machines to distant planets. It's about redefining civilization, encountering the unknown, and adapting to environments that will shape new ways of living, thinking, and existing. Our path forward will be a blend of scientific discovery, engineering marvels, and profound philosophical shifts that will reshape human life in ways we are only beginning to imagine. One of the most critical areas of focus is the development of long-term, self-sustaining colonies on other worlds, starting with the Moon and Mars. These early outposts will be the testbeds for the technologies and systems needed for humanity to become a truly multi-planetary species. Lunar bases will likely be the first permanent human settlements outside Earth, with the Moon serving as an ideal platform for testing life support systems, habitat designs, and in-situ resource utilization. ISRU technologies. ISRU involves using local materials such as lunar regolith or ice deposits for construction, oxygen production, and fuel generation. By harnessing the Moon's resources, we can reduce reliance on Earth, making future missions to Mars and beyond more feasible. The Moon's proximity also makes it an ideal location for building the infrastructure necessary for deep space exploration. NASA's Artemis program, along with international and private partners, is aiming to establish a sustainable human presence on the Moon. The Lunar Gateway, a space station planned to orbit the Moon, will act as a hub for astronauts and cargo, supporting lunar surface missions and serving as a launch point for journeys to Mars. This infrastructure will be essential for developing the technologies and capabilities needed for deep space travel, providing a testing ground for habitats, transportation systems, and even agricultural systems that will eventually support longer missions. While the Moon provides an accessible and practical starting point, Mars represents the next great leap. The red planet's more Earth-like day length and the presence of water ice make it a prime target for colonization. The architecture of Mars missions is evolving, with SpaceX's Starship and NASA's concepts for human habitats leading the way. Initial missions will focus on building infrastructure, such as inflatable habitats or structures built using Martian soil and 3D printing technology. These missions will test the feasibility of producing food, generating oxygen, and creating fuel directly from Martian resources, such as converting carbon dioxide from the atmosphere into methane fuel using the Sabatier process. The creation of Martian colonies will not just be a technological challenge. It will be a social and cultural experiment. Future settlers on Mars will be pioneers in every sense, living in isolation from Earth for months or even years at a time. The psychological and social dynamics of these isolated communities will be critical to their success. To prepare, space agencies are already conducting simulations on Earth, such as the HIC's missions in Hawaii, where crews live in Mars-like conditions for extended periods. These simulations help researchers understand how isolation, confinement, and stress affect group dynamics and individual mental health, allowing them to develop strategies to support well-being during real missions. One potential solution to the challenges of long-term isolation in space is the integration of advanced virtual and augmented reality technologies. These technologies could provide astronauts with simulated Earth environments, allowing them to experience nature, interact with loved ones, or explore new worlds virtually, all from within the safety of their habitats. Immersive VR experiences could help combat the monotony and psychological effects of being confined in small spaces for extended periods. Beyond just entertainment, augmented reality could also be used for training and repair missions, guiding astronauts through complex tasks in real time using overlays and instructions. As we move from Earth's orbit and the lunar surface to Mars and beyond, the notion of autonomy and artificial intelligence, AI, becomes increasingly important. Space missions, especially those involving humans, must function autonomously to a high degree due to the communication delays with Earth. AI-driven systems will manage life support, monitor habitat conditions, and assist with medical needs. Robots and AI companions could provide assistance and even companionship to astronauts, making life on Mars or other distant locations more manageable. Autonomous rovers like Perseverance on Mars have already demonstrated the power of these technologies, and future missions will rely even more heavily on AI to navigate, explore, and conduct scientific research in hostile environments. The concept of bioengineering is also gaining traction as we think about how to adapt both humans and plants to the harsh conditions of space. Scientists are exploring ways to genetically modify plants to thrive in low-gravity, high-radiation environments, ensuring a stable and diverse food supply for future colonies. By enhancing the resilience of crops like wheat, potatoes, and leafy greens, we can create agricultural systems that can operate in environments vastly different from Earth's. Additionally, researchers are investigating the possibility of using microbes engineered to produce oxygen, recycle waste, or build materials for habitat construction. These biological systems could create a sustainable ecosystem within space colonies, reducing the need for resupply missions from Earth. Human bioengineering is a more controversial but increasingly discussed possibility. Modifying humans to be more resistant to radiation, to cope with low-gravity environments, or even to adapt to different atmospheric compositions could make long-term space habitation more feasible. However, the ethical implications are immense. The question of whether we should genetically alter humans for space travel touches on fundamental concerns about identity, consent, and the nature of humanity. The potential to create space-adapted humans could lead to societal divides between those who choose or are chosen for these modifications and those who remain on Earth. As the reality of long-term space travel becomes imminent, these ethical debates will need to be addressed, with international consensus on how such technologies are regulated and applied. Moving beyond Mars, the outer planets and their moons present new frontiers. Missions to the Jovian system, specifically Europa, will seek to explore the ice-covered ocean world for signs of life. Europa's potential as a habitat is intriguing. Its subsurface ocean, protected by an icy shell, might harbor conditions suitable for life. Future missions like NASA's Europa Clipper will study the moon's surface and environment, and plans for landers capable of drilling through its ice are in development. The discovery of life in Europa's ocean, even if only microbial, would have profound implications, proving that life can arise independently in multiple locations and dramatically increasing the likelihood that the universe is teeming with life. Titan, Saturn's largest moon, offers another fascinating environment for exploration and possibly colonization. Its thick atmosphere and surface lakes of liquid methane present an environment radically different from Earth, yet it also possesses a unique appeal. Missions like Dragonfly, a drone designed to explore Titan's surface, will investigate its chemistry and look for prebiotic conditions that could reveal how life might arise under such extreme conditions. Titan's abundant organic compounds make it a potential site for future research and resource utilization, and understanding its atmospheric and geological dynamics could help us prepare for environments elsewhere in the galaxy. The expansion into space inevitably raises questions about planetary protection and ethical stewardship. As we extend our reach, the potential to contaminate other worlds with Earth organisms grows. Strict protocols are in place to prevent forward contamination, but as human activity in space increases, ensuring these protocols are effective becomes more difficult. We must also consider backward contamination, protecting Earth from any potentially harmful organisms that might be brought back from missions to Mars or other planets. These biosecurity measures will be vital in ensuring that exploration does not lead to unintended consequences, both on Earth and in the environments we encounter. The search for life, both within our solar system and beyond, continues to drive much of our exploration. The discovery of even the simplest microbial life would redefine biology and confirm that life is not unique to Earth. Advanced telescopes and probes are being designed to look for biosignatures, signs of life, on exoplanets, with missions targeting atmospheres of distant planets to detect gases like oxygen, methane, and other molecules that might indicate biological activity. The James Webb Space Telescope and its successors will play key roles in this search, and future missions may send small robotic explorers or even bioprobes capable of searching for and studying life forms in distant star systems. In parallel, the idea of human interstellar travel, while still futuristic, is gaining more attention. Concepts like the Breakthrough Starshot Initiative propose sending tiny, lightweight probes to the nearest star systems using powerful laser propulsion, potentially reaching Alpha Centauri within a few decades. These missions aim to demonstrate the feasibility of reaching other stars and will pave the way for more ambitious efforts to explore exoplanets up close. Interstellar travel, however, raises questions about time, distance, and the nature of human experience, as voyages to other stars may take centuries. The idea of generation ships, self-sustaining habitats that travel for generations, presents both opportunities and challenges, as it would involve the creation of entirely new societies in transit. The expansion of humanity into space will undoubtedly redefine what it means to be human. As we move beyond Earth, we will encounter not only physical challenges but also cultural and philosophical transformations. Space colonies may develop their own identities, values, and cultures, distinct from Earth's, shaped by the unique conditions and experiences of living beyond our home planet. The evolution of these space societies will challenge traditional concepts of nationality, culture, and governance, leading to a future where Earth may be seen as the birthplace of humanity, but not its final destination. In this vast cosmic journey, the possibilities are as limitless as the stars themselves. Whether we find life, build new societies, or discover technologies that reshape our understanding of the universe, the future of space exploration holds the promise of a new era for humanity, one where the boundaries of Earth no longer confine our aspirations or our potential. The universe is not just a destination. It is an invitation to grow, to evolve, and to explore the limitless horizons of existence. As we step into this new chapter, we carry with us the curiosity, ingenuity, and resilience that have defined humanity's greatest achievements, propelling us forward into the unknown with the promise of discovery and the hope of an ever-expanding future. As humanity stands on the threshold of becoming a space-faring civilization, the journey ahead is both thrilling and fraught with complexity. The cosmos is not just a realm to be explored, but a vast expanse that challenges us to rethink every aspect of human life, from technology and survival to culture and identity. Our next steps will be crucial, shaping the destiny of our species as we expand beyond Earth. This final frontier is not only a place of scientific and technological adventure, but also a stage for the evolution of human society in ways that we can scarcely imagine. The challenges we face will push us to innovate, adapt, and evolve in response to the immense, unforgiving, yet awe-inspiring expanse of space. One of the key areas of focus for future missions will be to develop advanced systems for building infrastructure in space, both in orbit and on planetary surfaces. The establishment of large-scale habitats, laboratories, and production facilities is essential for sustaining long-term human presence beyond Earth. A significant leap in this regard is the concept of in-situ construction using automated robots and 3D printing technologies. These systems will allow us to build habitats and other structures using materials found on the Moon, Mars, or asteroids. The ability to construct infrastructure directly on-site will be a game-changer, reducing the need to launch heavy materials from Earth and making space colonization economically and logistically viable. On the Moon, regolith, the dusty material covering its surface, can be used as a raw material for building blocks and other essential structures. Lunar dust is rich in metals and minerals, and experiments have shown that it can be processed to create bricks and other construction materials through additive manufacturing techniques. Robotic builders will be deployed to automate the process, constructing habitats that protect future settlers from radiation, extreme temperatures, and micrometeorite impacts. As we perfect these techniques on the Moon, we will gain the experience and technology needed to build similar structures on Mars and eventually beyond. Mars presents its own unique challenges and opportunities for construction. The Martian atmosphere, while thin and inhospitable for humans, contains carbon dioxide, which can be utilized for producing building materials such as carbon fiber. This material is lightweight, strong, and can be manufactured directly on Mars, enabling the construction of large, resilient structures. Additionally, scientists are exploring the potential of using local basalt rock, which is abundant on Mars, to create sustainable building materials through 3D printing. These innovations will allow Martian habitats to be both resource-efficient and highly adaptive to the planet's environment. The future of human presence on Mars and other celestial bodies will not rely solely on stationary habitats. The idea of mobile habitats or rovers capable of supporting human life over long distances is gaining traction. These mobile bases would allow astronauts to explore and conduct scientific missions across vast stretches of Mars' surface or other planets. They could be designed as modular, self-sustaining units equipped with life support systems, power generation, and laboratories for on-site analysis. This mobility would be crucial for exploring diverse regions of Mars, including its polar ice caps, ancient riverbeds, and vast plains, all of which hold clues to the planet's history and its potential for life. For any long-term presence on Mars or other planets, transportation between Earth, Moon, and Mars must become routine and efficient. SpaceX's Starship and other reusable rocket systems are paving the way for this new era of space travel, reducing the cost and time associated with sending people and cargo between planets. However, as these systems become operational, the need for advanced refueling stations and spaceports in orbit will grow. These spaceports could be constructed in Earth's orbit, at the Lunar Gateway, and eventually in Mars orbit, acting as logistical hubs where spacecraft can refuel, dock, and transfer cargo. The development of a network of these stations will be the backbone of an interplanetary transportation system, supporting regular missions and the expansion of human colonies. Beyond Mars, the outer reaches of our solar system offer a wealth of resources and scientific opportunities. The asteroid belt, located between Mars and Jupiter, contains vast quantities of metals, water ice, and other valuable materials. Future missions aim to establish robotic mining operations on these asteroids, extracting resources for use in space construction, fuel production, and even Earth-based markets. Companies and space agencies are developing the technology needed for these mining missions, including autonomous spacecraft capable of navigating the asteroid belt, anchoring to asteroids, and harvesting materials with minimal human intervention. The success of these missions could transform space into a thriving economic zone, supporting the construction of massive space stations, ships, and even space cities. The establishment of space cities is not purely theoretical. The concept of O'Neill cylinders, large rotating habitats designed to simulate Earth-like gravity, is being revisited with modern technology and materials. These massive space habitats, potentially hosting thousands or even millions of people, could orbit in various locations, including around Earth, Mars, or in the asteroid belt itself. They would function as self-sustaining communities with their own economies, agriculture, and industry, and they could serve as hubs for scientific research, trade, and deep space exploration. Building these cities would require a new level of cooperation between nations and private companies, as well as the development of technologies that allow for the recycling of materials, closed-loop life support systems, and advanced manufacturing capabilities. As we extend our reach into space, the issue of governance and the political landscape of space will become increasingly important. The current international space treaties, such as the Outer Space Treaty, provide a framework for cooperation and the peaceful use of space. However, they were created during a time when only governments were involved in space activities. The rise of private space companies and the potential for space tourism, mining, and colonization necessitate new laws and regulations that address the rights of companies, nations, and individuals in space. This will involve determining how resources are shared, how territories are managed, and how new societies in space are governed. As humanity moves toward a multi-planetary future, a global consensus will be needed to ensure that space remains a domain for peaceful exploration and mutual benefit. While the practical aspects of space expansion are paramount, the cultural and social implications of becoming a spacefaring species are equally profound. Space colonies will not just be isolated outposts. They will be the birthplaces of new cultures, identities, and communities. The children born in these colonies may never know Earth as their home and will likely develop their own sense of identity, shaped by the environment and experiences unique to life beyond Earth. This cultural evolution will raise questions about how humanity defines itself. Will Earth remain the cultural and political center of humanity, or will new centers emerge as space colonies become independent and self-sufficient? Space exploration also has the potential to unite humanity under a shared goal. The effort to explore and settle other planets requires collaboration between nations, organizations, and individuals. International partnerships like the International Space Station (ISS) have already demonstrated the power of cooperation in space, bringing together diverse groups with a common mission. As we expand to the Moon, Mars, and beyond, these partnerships will need to evolve, creating a framework for joint missions, shared resources, and mutual support. The pursuit of space colonization could become a unifying force, promoting global collaboration and a shared vision for the future of humanity. The search for life beyond Earth remains one of the most tantalizing aspects of space exploration. Missions to Mars, Europa, and Titan are designed to seek out signs of life, past or present, in these distant environments. The discovery of microbial life on another world would fundamentally alter our understanding of biology and the origins of life, opening up the possibility that life is widespread across the universe. Such a discovery would not only be a scientific breakthrough, but a profound cultural and philosophical event, prompting humanity to reevaluate its place in the cosmos. The question of whether life exists elsewhere also drives efforts to send probes and telescopes beyond our solar system, scanning exoplanets for atmospheres and conditions that could support life. The detection of intelligent extraterrestrial civilizations, should it occur, would be even more transformative. The idea that we are not alone in the universe has fascinated and perplexed humans for centuries, but the implications of actual contact are complex. How would we communicate with another civilization, and what would such a contact mean for human society? Would it unite humanity or cause division? The discovery of intelligent life would present both incredible opportunities for learning and cooperation and significant challenges, as we navigate the uncertainties of interacting with beings whose intentions and nature may be entirely unknown. Humanity's expansion into space is the next great chapter in the story of civilization. The journey will be filled with unprecedented challenges and opportunities that will test our ingenuity, our capacity for cooperation, and our willingness to evolve. As we build new homes among the stars, develop the technology to traverse the vastness of the cosmos, and perhaps even encounter other forms of life, our identity as a species will be reshaped. We will not just be citizens of Earth, but citizens of the universe. In this new era, the cosmos becomes more than just a frontier for exploration. It becomes a canvas for the next evolution of human society. The story of space is not only a scientific and technological pursuit, it is the unfolding of humanity's ultimate adventure, a quest that will transform not just how we live, but who we are. As humanity stands on the cusp of its grand adventure into the cosmos, every step forward will redefine our existence, pushing the boundaries of technology, society, and the very nature of human life. The journey to become a multi-planetary species involves not just adapting to new environments, but also building new frameworks for how civilizations operate, interact, and grow far beyond Earth. The vastness of space is not just an opportunity to explore and colonize, but a chance to reimagine what it means to be human, to collaborate on a scale never seen before, and to confront the mysteries of life and existence on a cosmic level. As we prepare to embark on this journey, several emerging trends and challenges highlight the future trajectory of human expansion into the cosmos. One of the most exciting developments is the concept of space elevators. For decades, space elevators have been a staple of science fiction, but they are gradually becoming a serious topic of engineering and technological research. A space elevator would involve a cable stretching from Earth's surface to a station in geostationary orbit, providing a more cost-effective and efficient means of transporting materials, cargo, and even people into space. The biggest challenge lies in developing a material strong enough to withstand the immense tension and forces acting upon it. Advances in carbon nanotubes and graphene technology offer some hope, as these materials are incredibly strong and lightweight, but the engineering requirements are still vast. If a space elevator were to become operational, it could revolutionize space travel by drastically reducing the cost of launching payloads and opening up space to greater commercial, scientific, and even tourism ventures. Parallel to these technological efforts is the development of advanced propulsion systems designed for interplanetary travel. Nuclear propulsion, both in the form of nuclear thermal and nuclear electric systems, promises to cut travel times significantly, making missions to Mars and beyond more feasible. However, even as these propulsion systems develop, there is a growing interest in exotic propulsion technologies such as antimatter drives and solar sails. Antimatter, which annihilates matter to produce massive amounts of energy, could theoretically power spacecraft at incredible speeds, enabling rapid travel across the solar system. Solar sails, which use the pressure of sunlight or laser beams to push spacecraft, are being tested for missions to explore the outer planets and even nearby stars. While these technologies remain in the experimental phase, their development represents a crucial step toward faster and more efficient space travel. One of the most transformative breakthroughs may come from the field of artificial intelligence, AI. AI systems will play a central role in the future of space exploration, managing everything from autonomous robotic explorers to life support systems on human missions. On long-duration missions to Mars, for example, the time delay in communications with Earth makes real-time decision-making impossible. AI must therefore handle complex tasks such as navigating terrain, conducting scientific experiments, and maintaining critical systems autonomously. The use of AI extends to orbital and planetary habitats, where it will monitor air quality, radiation levels, and habitat integrity, ensuring that human settlers can live safely and efficiently. In the future, AI might even manage entire colonies, optimizing resource use and supporting the daily needs of thousands of inhabitants. As we expand human presence into space, bioengineering will become an increasingly important tool for adapting both humans and plants to alien environments. On Earth, scientists are already using CRISPR and other genetic modification techniques to enhance crops, making them more resistant to diseases and environmental stressors. In space, this technology could be applied to modify plants so they can grow in low-gravity conditions or withstand the higher radiation levels found on Mars or the Moon. Bioengineered plants could produce not only food, but also essential materials like bioplastics, oxygen, and medicine, forming the backbone of life support systems for space colonies. The prospect of bioengineering extends beyond plants. There is active discussion about modifying human biology to better suit space environments. Genetic modifications that increase resistance to radiation, reduce muscle atrophy in low-gravity environments, or even enhance bone density could make long-term habitation on Mars or deep space missions more viable. However, these modifications bring up ethical and societal questions. The development of space-adapted humans could create divides between those who choose to remain unaltered and those who undergo genetic enhancements, raising concerns about inequality and the evolution of human identity. Regulatory frameworks and ethical guidelines will be necessary to navigate the implications of such technologies as they become more advanced and widespread. As humanity moves further from Earth, the ability to create self-sustaining ecosystems in space habitats and colonies will be vital. The concept of closed-loop life support systems, which recycle air, water, and waste to sustain human life, is being refined on the International Space Station, ISS, and will be crucial for future missions to Mars and beyond. On Earth, efforts are already underway to create biospheres that simulate self-contained ecosystems. These projects, while still experimental, provide valuable insights into how plants, bacteria, and even insects can be integrated to maintain balance and produce food, oxygen, and water. Applying these concepts on Mars or in space stations will allow humanity to build truly self-sustaining colonies, reducing reliance on Earth's resources. Energy generation in space is another essential factor for the success of future colonies. Solar power is effective near Earth and Mars, where sunlight is abundant. But as we move further out, new solutions are required. Nuclear power, particularly nuclear fusion, is a promising avenue. While fusion technology is still in development, its potential to provide massive amounts of energy with minimal fuel is a game changer. Successful deployment of fusion reactors in space could power habitats, spacecraft, and entire colonies, supporting large-scale industrial operations and long-term habitation. In parallel, scientists are exploring other methods like space-based solar power, which involves collecting solar energy in space and beaming it back to Earth or other locations using microwaves. Such technology could not only provide power for space missions, but also offer a clean energy solution for Earth. The establishment of industries in space will transform the economy of the cosmos, turning it into a thriving domain of human activity. Asteroid mining, for instance, is becoming an increasingly viable prospect, with companies developing robotic mining technology to extract metals and water from asteroids. The water found in asteroids can be split into hydrogen and oxygen, providing fuel for spacecraft and supporting life support systems. Metals and minerals can be used in space manufacturing, creating tools, machinery, and even large structures without needing to launch them from Earth. The economic potential of asteroid mining is immense, with estimates suggesting that the value of resources in the asteroid belt alone could be worth trillions of dollars. The growth of this space economy will likely drive the development of new technologies and infrastructure, enabling the construction of large space habitats and interplanetary transport systems. However, with the rise of a space economy, the issue of ownership and governance becomes critical. Who controls the resources of space? How are they shared? And who benefits? The current legal framework, based on treaties established during the early space age, is insufficient to handle the complexities of a commercial and industrial presence in space. New international agreements will be needed to ensure that space remains a domain for peaceful and equitable use. These agreements must balance the interests of private companies, nations, and international organizations, setting guidelines for mining, colonization, and the establishment of space cities. It is essential to prevent conflicts and ensure that the benefits of space exploration are distributed fairly among all humanity. As the space economy grows, so too will the possibilities for space tourism and civilian space communities. Companies like SpaceX, Virgin Galactic, and Blue Origin are already pioneering commercial space travel, with plans to offer orbital hotels and lunar vacations. As these ventures become more common, space tourism will not only become a luxury for the wealthy, but could also evolve into a stepping stone for people from all walks of life to experience space. The development of affordable, reusable spacecraft is crucial for this transformation, making space accessible to a broader population and fostering a culture of exploration. Civilian space communities, groups of people living and working in orbital habitats or lunar colonies, will also emerge, creating a new demographic of people who live their daily lives beyond Earth. The cultural and social evolution of these space communities will be fascinating to observe. People born and raised on Mars, for example, may develop a unique culture distinct from Earth's, shaped by the harsh environment and the need for collaboration and resilience. The growth of these societies will raise questions about identity, governance, and the relationship between Earth and its colonies. Will space colonies operate as extensions of Earth's nations, or will they become independent entities with their own laws and governance structures? The evolution of space societies will test humanity's ability to build new forms of community and cooperation in environments that demand innovation and adaptability. Finally, the search for extraterrestrial life will continue to be a driving force in our exploration efforts. Missions to Europa, Titan, and exoplanets beyond our solar system will aim to find signs of life or conditions conducive to its existence. The discovery of life elsewhere, whether microbial or intelligent, would be the most significant event in human history, fundamentally altering our understanding of life, evolution, and the universe. If we do find life, the implications for philosophy, religion, and society will be profound. We will need to navigate the ethical considerations of how we interact with or study these new forms of life, while also grappling with the possibility that we are not alone in the cosmos. In this bold, new era of exploration, the cosmos offers infinite possibilities. Humanity's journey into space is not just about technology and survival. It is a journey of discovery, transformation, and growth. As we expand our presence beyond Earth, the challenges will be immense, but so too will be the opportunities for collaboration, innovation, and the creation of new societies. This adventure will reshape human identity, pushing us to think beyond the boundaries of Earth and embrace the vast, interconnected cosmos as our home. The stars await, and with them, the next great chapter in the story of human civilization. As humanity progresses further into the cosmos, each new chapter in our journey becomes more intricate, filled with unprecedented possibilities and the complexities that come with expanding our existence beyond Earth. The challenge is not merely about technological advancements. It's about fundamentally redefining how we live, interact, and evolve as a species spread across multiple worlds and environments. The vastness of space is as much a test of human ingenuity and resilience as it is an invitation to explore new horizons. As we prepare to expand into the stars, the evolution of our civilization will be marked by profound changes in technology, culture, and our understanding of the universe and ourselves. One of the first critical challenges we face is developing sustainable living systems for space habitats, not just for short-term missions but for permanent colonies. On the Moon, the establishment of lunar bases will be our initial testbed for these systems. Plans for habitats such as NASA's Artemis Base Camp and other international projects focus on utilizing local resources, like extracting water ice from lunar craters and converting regolith into building materials. Lunar ice can be split into hydrogen and oxygen, not only providing drinking water and breathable air, but also fueling rockets for missions to Mars and beyond. Building a self-sustaining lunar economy will be a stepping stone, allowing us to develop the skills, technology, and infrastructure necessary for long-term habitation. As we look to Mars, the stakes are even higher. The Martian environment is harsh, with extreme temperatures, a thin atmosphere, and high levels of radiation. To create habitable conditions, scientists are exploring the use of radiation-shielded domes or underground habitats built into the Martian surface. These structures would protect colonists from harmful cosmic rays and the Martian dust storms that periodically sweep across the planet. Underground habitats are particularly promising, as they can provide natural insulation and stability. Future colonists might live in vast networks of underground cities connected by tunnels, with artificial lighting, controlled climates, and advanced life support systems to simulate Earth-like conditions as closely as possible. The development of agriculture on Mars is another key focus. To sustain long-term human presence, we must grow food locally, reducing dependency on Earth supplies. Research on Earth, particularly in controlled environments like greenhouses and vertical farms, is paving the way for Martian agriculture. Scientists are experimenting with Martian soil simulants to test the growth of crops like potatoes, tomatoes, and lettuce, as well as more resilient plants such as algae and spirulina that could thrive under Martian conditions. The success of these agricultural systems will be essential for creating a stable and diversified food supply, ensuring that Mars colonies can not only survive but thrive independently. Genetic modification may play a vital role in adapting crops and organisms to space environments. By engineering plants to withstand low-light conditions, grow in nutrient-poor soils, or even absorb higher levels of radiation, we can develop agricultural systems tailored specifically for Mars or other celestial bodies. Similar techniques could be used for bioengineering microbes capable of converting Martian soil into fertile ground or producing essential nutrients and medicines. These biological innovations would form the backbone of self-sustaining ecosystems, integrating agriculture, waste recycling, and life support functions into a single, closed-loop system that supports human life far from Earth. Beyond technological and biological adaptations, The next frontier in space habitation will involve the integration of advanced robotics and AI. Robots will be the first inhabitants of Mars, building habitats and infrastructure before humans arrive. Autonomous robots and drones will operate construction machinery, dig foundations, and assemble habitats using materials extracted from the Martian surface. In this way, the construction of Mars bases will be largely automated, minimizing the risk to human workers and optimizing efficiency. AI-driven systems will manage everything from habitat conditions to agricultural cycles, ensuring that life support systems function optimally and adapt to any unforeseen circumstances, such as equipment malfunctions or environmental changes. These automated systems won't just be functional. They'll become an integral part of daily life for human settlers. AI companions, robots designed not just for utility but also for interaction, could assist colonists with tasks, monitor health, and even provide social interaction. In environments where human contact is limited, such as the confined spaces of a Martian habitat or a spacecraft en route to distant planets, AI companions could help alleviate the psychological stresses associated with isolation. By providing both practical support and a degree of companionship, these systems could improve the well-being of astronauts and colonists, making long-term missions more sustainable and less isolating. As colonies grow and expand, the concept of interplanetary trade will emerge. The Moon, Mars, and asteroid mining operations could create a network of resource exchanges that support the growth of space cities and industries. Lunar bases, for example, could specialize in mining and refining metals needed for building materials, while Mars might become an agricultural hub, producing food and oxygen for other colonies. Asteroids rich in rare metals, like platinum and gold, could be mined and transported back to Earth or used directly in space manufacturing facilities. This exchange of resources and goods between different planets and moons will form the basis of a space economy, a complex web of trade and production that transcends Earth's boundaries. The evolution of this space economy raises critical questions about governance and law. As colonies establish themselves, the current framework of international space law, primarily based on treaties like the Outer Space Treaty, will need to evolve. New regulations will have to address the ownership of resources, the rights of colonists, and the legal status of new settlements. Who will own the resources mined from asteroids or Mars? How will conflicts be resolved in space? And what kind of legal systems will be in place for colonies millions of miles from Earth? The creation of a fair and sustainable governance model will be crucial to prevent conflicts and ensure that the expansion into space benefits all of humanity, not just a select few. Alongside these practical and legal developments, the cultural and societal transformation of space colonies will be profound. As humans establish themselves on Mars, the Moon, or in space habitats, entirely new cultures and identities will emerge. Martian colonists, for example, may develop their own traditions, values, and ways of life, shaped by the unique challenges and environment of the Red Planet. These space communities will need to foster a strong sense of collaboration and adaptability, as survival in such harsh conditions will depend on collective effort and resourcefulness. Over time, these colonies may even become independent from Earth, developing their own political systems and becoming self-governing entities with distinct identities and aspirations. The rise of space cities, large, self-sustaining habitats in orbit or on planetary surfaces, will be a critical milestone in this evolution. These cities will be more than just functional outposts. They will be places where people live, work, and build new societies. Advanced habitats like O'Neill cylinders or Stanford Torrey will simulate Earth's gravity through rotation and provide environments that closely mimic Earth's natural landscapes, complete with rivers, forests, and fields. Such habitats will offer the opportunity for millions of people to live in space, creating urban centers that serve as hubs for industry, culture, and education. As these space cities grow, they may become centers of innovation, producing technologies and cultural developments that influence not only space colonies but also life on Earth. The exploration of the outer planets and their moons will also be crucial in humanity's expansion. Jupiter's moon Europa, with its subsurface ocean, and Saturn's moon Titan, with its thick atmosphere and lakes of methane, offer tantalizing possibilities for scientific research and even colonization. Missions designed to explore these moons will need specialized technology capable of drilling through Europa's ice or navigating Titan's hydrocarbon seas. The discovery of life, or the conditions for life, on these moons would be a monumental event, reshaping our understanding of biology and the potential for life beyond Earth. Colonies on these moons could serve as research bases and launch points for further missions to the outer reaches of our solar system. The ultimate goal for humanity may not be limited to our solar system. With the discovery of thousands of exoplanets, including those in the habitable zones of their stars, interstellar travel has become a more serious consideration. Concepts such as Breakthrough Starshot, which aims to send tiny spacecraft to nearby star systems using powerful laser propulsion, represent the first steps toward exploring these distant worlds. While reaching another star system remains a monumental challenge, the development of advanced propulsion technologies, like fusion drives or antimatter engines, could one day make interstellar missions possible. Such missions would open the door to colonizing exoplanets and potentially encountering other forms of life. The discovery of intelligent extraterrestrial civilizations, if it happens, would be the most transformative event in human history. The implications of such contact are vast, ranging from the exchange of knowledge and technology to the challenge of understanding and interacting with entirely alien cultures. The question of how humanity would approach and respond to such a discovery is central to the ongoing search for extraterrestrial intelligence. Should we actively seek to communicate with other civilizations, or should we proceed with caution, given the potential risks? The answers to these questions will shape the future of humanity's interaction with the cosmos. Ultimately, the expansion into space is not just about technology, survival, or even the search for life. It is about the evolution of human civilization on a cosmic scale. The challenges we face will force us to innovate, adapt, and reimagine what it means to be human. As we establish ourselves on new worlds and build societies far from Earth, we will encounter opportunities to create new forms of culture, cooperation, and governance that transcend the limitations of our home planet. The cosmos is not just a place to explore. It is the next chapter in the human story, a canvas upon which we will paint the future of our species. The stars call us, and as we answer, we carry with us the promise of discovery, growth, and a new era of human civilization that reaches beyond Earth and into the infinite expanse of the universe. As humanity's reach extends further into the cosmos, the journey ahead is not merely about physical expansion, but also about philosophical, cultural, and existential transformation. Each new frontier pushes the boundaries of what we know, tests our adaptability, and reshapes the very foundation of our civilization. Space is not simply a destination. It is a vast, evolving canvas that invites humanity to rethink its place in the universe. As we move beyond Earth, the technologies we develop, the societies we build, and the discoveries we make will have profound impacts on our identity, our values, and the future trajectory of humanity. This adventure into space will be defined by innovation, cooperation, and an evolving sense of what it means to be human. The development of advanced space habitats, capable of supporting long-term human life in orbit or on planetary surfaces, remains a cornerstone of our future plans. While initial efforts focus on habitats that use inflatable modules or underground Martian structures for radiation shielding, longer-term ambitions involve creating large, Earth-like environments. The vision of building massive, rotating habitats, such as O'Neill cylinders, where people can live in gravity-simulating conditions, is becoming more feasible as engineering technologies advance. These structures would spin to create artificial gravity, replicating Earth's conditions and allowing for the development of agriculture, industry, and entire communities. These space habitats will not only be functional, but will also aim to recreate the familiar comforts of Earth, such as parks, water features, and even artificial skies to simulate day and night cycles. Psychologists and architects are working together to design habitats that minimize the effects of isolation and confinement, which are common in current space missions. By incorporating green spaces, recreational areas, and social hubs, these environments will help foster a sense of community and well-being, which is essential for the long-term sustainability of space colonies. Living in these advanced habitats may eventually feel much like living in an urban environment on Earth, albeit with the thrill and challenge of being far from our home planet. As space habitats evolve, the social dynamics within these communities will become increasingly complex. These new societies will have to develop norms and cultural practices suited to life in the extreme and often isolated conditions of space. The creation of governance systems that are both fair and functional will be a key challenge. How do we manage resources fairly when they are scarce? How do we establish laws and justice systems in environments where a single mistake can threaten the survival of an entire community? And as these colonies grow, the question of independence becomes relevant. Will Martian colonies, for instance, eventually seek autonomy from Earth, developing their own political systems and identities? This brings us to the concept of space citizenship and the legal frameworks needed for these new societies. The rise of space colonies will likely require the establishment of new governance models, blending elements of international law with entirely new systems designed for space. The development of a space constitution might become necessary, laying out the rights and responsibilities of citizens living in space habitats or on other planets. This constitution could address issues like resource distribution, the right to self-governance, and even the establishment of interplanetary trade laws. The creation of such a framework would require international cooperation, as well as the input of experts in law, ethics, and human rights, to ensure that space remains a domain for peaceful coexistence and equitable opportunities. In tandem with these social and legal developments, the technology for transportation and logistics will continue to evolve. The goal is to establish a reliable and efficient transportation network connecting Earth, the Moon, Mars, and other locations within our solar system. Spaceports will become hubs of activity, facilitating the movement of goods, resources, and people. Refueling stations using lunar ice or Martian resources will support spacecraft on their long journeys, and spacecraft designs will advance to become fully reusable and capable of landing on a variety of celestial bodies. The success of such a network will be crucial for sustaining colonies and enabling economic growth, as the transport of resources between planets becomes a standard operation. The expansion of a space economy goes beyond transportation. Asteroid mining, for example, is poised to become a key industry. Asteroids contain vast amounts of valuable metals like platinum, nickel, and rare earth elements, which are essential for advanced technologies. Extracting these materials will not only fuel the development of space industries, but also reduce the need for Earth-based mining, which has significant environmental impacts. Robotic mining missions will be the first to tap into these resources, with autonomous systems navigating asteroid fields, anchoring to rotating bodies, and extracting metals and water ice. As these technologies develop, the concept of space foundries, facilities that process and refine these materials in orbit, will emerge, allowing construction projects to be completed without the need for materials launched from Earth. This economic growth will be bolstered by manufacturing in space. With the development of advanced 3D printing and additive manufacturing technologies, entire structures can be built in orbit using locally sourced materials. This capability will transform space construction, allowing habitats, satellites, and even spacecraft to be built directly in space, reducing costs and increasing flexibility. Factories in orbit could produce solar panels, components for space habitats, and even consumer goods, creating a new economy that supports both Earth and space-based societies. The expansion of these industries will be a key driver of economic activity, pushing humanity toward becoming a multi-planetary species with an interplanetary economy. The evolution of the space economy and the establishment of colonies raise critical ethical and environmental questions. The potential to harm or contaminate other planets and moons is a significant concern. As humanity begins mining and colonizing other celestial bodies, the importance of planetary protection protocols becomes paramount. These protocols aim to prevent the contamination of other worlds with Earth-based organisms, as well as ensuring that Earth remains safe from potential extraterrestrial microbes brought back by missions. As space activities increase, the development of more sophisticated biosecurity measures will be crucial. involving quarantine systems, sterilization technologies, and strict regulations for missions that interact with alien environments. The rise of space tourism and commercial spaceflight will also play a major role in shaping the future of space. Companies are developing plans for orbital hotels, lunar vacations, and even visits to Mars for adventurous tourists. As space tourism becomes more accessible, it will drive the development of safer, more affordable spacecraft and create new opportunities for ordinary people to experience space. The influx of tourists and settlers will accelerate the growth of spaceports, hotels, and entertainment facilities in orbit and on the Moon. This expansion will not only make space travel more common, but will also help normalize life in space, gradually transforming it from an exclusive domain of astronauts and scientists into a realm where people from all walks of life can participate. As more people travel to space, the need for robust health and medical systems becomes critical. Space medicine is an evolving field that addresses the unique challenges posed by living in low-gravity environments and high-radiation conditions. Research is underway to develop treatments and preventive measures for conditions such as muscle atrophy, bone density loss, and vision impairment, which are common in space. Long-term space missions and colonies will also require advanced medical facilities capable of handling emergencies and providing routine care far from Earth hospitals. Bioengineering and genetic therapies may become standard for space settlers, enhancing their bodies to better withstand the rigors of space. This integration of technology and biology could redefine healthcare and human physiology in ways that extend beyond space exploration. One of the most profound aspects of our future in space is the search for extraterrestrial life. As missions to Europa, Enceladus, and other ice-covered moons continue, humanity might soon uncover signs of microbial life in the subsurface oceans of these distant worlds. The discovery of life, even in its simplest forms, would be transformative, suggesting that life could be common throughout the universe. It would prompt a re-evaluation of our place in the cosmos, as well as our ethical responsibilities when interacting with other life forms. Such a discovery would not only be a scientific breakthrough, but also a philosophical and cultural shift, impacting how humans see themselves and their role in the universe. Beyond our solar system, the search for exoplanets continues to yield exciting discoveries. With advanced telescopes like the James Webb Space Telescope and future missions planned for exoplanet exploration, astronomers are getting closer to finding Earth-like planets in the habitable zones of their stars. Detecting biosignatures such as oxygen, methane, or water vapor in the atmospheres of these distant worlds could indicate the presence of life. As technology advances, humanity might one day send probes to these exoplanets, or even develop technologies that allow us to visit them in person, marking the beginning of interstellar exploration. Interstellar travel, while still a distant goal, is an area of active research. Concepts such as the warp drive, inspired by Einstein's theory of relativity, and the development of laser-propelled light sails aim to make faster-than-light travel possible. The Breakthrough Starshot Initiative, for example, proposes sending tiny, laser-powered probes to the nearest star systems, which could provide humanity with its first close-up look at planets beyond our solar system. If successful, these missions will lay the groundwork for more ambitious projects, possibly including generation ships, self-sustaining habitats designed for multi-generational travel that could carry humans to distant stars. The ultimate question is, what will humanity find when it reaches the stars? The discovery of intelligent extraterrestrial civilizations, if it occurs, would be the most significant event in human history. Such a discovery could unite humanity in its quest to understand our place in the cosmos, or, alternatively, raise profound challenges as we learn to interact with another species. The implications for culture, religion, science, and international relations would be enormous as humanity grapples with the reality that we are not alone in the universe. Humanity's journey into space is not just about technology and discovery. It is about the evolution of human society and the reimagining of our existence on a cosmic scale. As we build new worlds, establish new societies, and expand into the vastness of space, we will face challenges that test our creativity, resilience, and cooperation. This journey will transform human culture, politics, and identity, reshaping our civilization and expanding our understanding of life and the universe itself. The cosmos is not just a frontier to explore. It is the next chapter in the human story, one that will define the future of our species and the legacy we leave as we step into the infinite possibilities of the universe. As humanity continues its grand journey into the cosmos, the expansion of our civilization beyond Earth becomes not just an engineering feat, but a profound transformation of society, culture, and the human condition itself. The vast, infinite realm of space is both a canvas and a challenge, one that requires us to rethink everything we know about survival, cooperation, and innovation. The transition from an Earth-bound species to an interplanetary and potentially interstellar civilization will unfold across multiple stages, each filled with opportunities and dilemmas that will shape our identity and legacy for centuries to come. One of the most immediate and practical steps is the expansion of our infrastructure in space, transforming Earth's orbit into a bustling hub of activity. The growth of space stations like the International Space Station, ISS, and its successors will continue, but with a shift toward commercial and modular designs. Companies such as Axiom Space are already developing private modules that can attach to the ISS and eventually detach to form independent commercial space stations. These stations will serve as research labs, tourist destinations, and production centers, laying the foundation for a space economy that supports life beyond Earth. Orbiting spaceports will become central nodes in this infrastructure. Acting as logistical and refueling hubs, these ports will facilitate transportation between Earth, the Moon, Mars, and other parts of our solar system. These spaceports will not only serve as waypoints for cargo and passenger flights, but also provide repair and maintenance services for spacecraft, extending the operational life of missions and equipment. These hubs will be essential for the growing space industry, which will include not only mining and manufacturing, but also agriculture, energy production, and even entertainment. The expansion into lunar and Martian territories will be driven by these advanced transportation networks. On the Moon, permanent bases will begin to develop into small cities, serving as research centers, mining operations, and launch points for further exploration. The Moon's resources, particularly water ice, will be critical in producing rocket fuel and supporting life in lunar habitats. As these cities grow, they will integrate advanced life support systems, power generation, and recycling technologies, forming self-sustaining ecosystems that support thousands of people. Mars, the next major target for colonization, presents both a significant challenge and opportunity. Initial missions to Mars will focus on scouting and developing essential infrastructure, such as creating a sustainable power grid using solar and nuclear power, establishing habitats capable of shielding against radiation, and implementing systems for water extraction and purification. The use of 3D printing and in-situ resource utilization, ISRU, technologies will be critical. These technologies will allow Martian settlers to construct buildings, tools, and vehicles directly from the planet's soil, significantly reducing reliance on supplies from Earth. As Martian colonies expand, they will become increasingly self-sufficient, with agriculture, manufacturing, and renewable energy systems evolving to support larger populations. The long-term success of Martian colonies will depend heavily on the development of closed-loop ecological systems. These systems will recycle water, air, and waste, integrating agriculture with waste management to create a self-sustaining cycle. Vertical farming, algae bioreactors, and genetically modified crops adapted to Martian conditions will form the basis of food production, ensuring a stable and diverse diet for colonists. These technologies will be optimized for resource efficiency, growing food with minimal water and energy while maintaining a high yield. Over time, these agricultural systems will expand beyond basic crops to include a wider variety of fruits, vegetables, and even livestock, supporting a more diverse and sustainable Martian ecosystem. The social and psychological dimensions of life on Mars will also require careful planning and innovation. Colonists will face the challenges of isolation, limited space, and the psychological impact of living in an environment that is both hostile and far from Earth. To mitigate these effects, Martian habitats will incorporate communal spaces, recreation areas, and virtual reality (VR) technologies that simulate Earth-like environments. These immersive VR experiences can offer colonists a chance to escape the monotony of their surroundings, simulating beaches, forests, or even cultural events from Earth, helping to maintain their mental well-being and sense of connection. As Martian society grows, so too will its identity. Over generations, those born and raised on Mars will likely see themselves not just as Earthlings living abroad, but as Martians, part of a distinct society with its own traditions, norms, and values. This cultural evolution will be influenced by the unique conditions of Martian life, such as the necessity for resourcefulness, cooperation, and resilience in the face of harsh environments. The Martian experience, shaped by long, cold nights, low gravity, and a reliance on artificial environments, will forge a culture distinct from Earth's, one that values innovation, adaptability, and a pioneering spirit. These settlers may create their own holidays, myths, and ways of life, all centered around the challenges and triumphs of building a new world. As Martian and lunar colonies become more established, the idea of interplanetary governance will become increasingly relevant. Questions about autonomy and independence will arise. Will these colonies remain under the jurisdiction of Earth-based nations, or will they seek self-governance and the formation of new political entities? As they grow more self-sufficient, these colonies will likely push for greater autonomy, leading to the creation of Martian or lunar republics with their own legal systems, constitutions, and representatives. This evolution will require the development of new treaties and agreements that balance the interests of Earth-based nations, private companies, and the rights of the colonists themselves. The creation of a United Nations of Space or an interplanetary federation could become necessary, offering a forum for the resolution of disputes, the regulation of trade, and the establishment of shared laws and standards that apply across multiple worlds. Such a federation would need to address complex issues like resource rights, environmental protection, and the fair distribution of economic benefits. It would also need to manage the relationship between Earth and its colonies, ensuring that the exploitation of space resources benefits all of humanity and does not lead to monopolization or conflict. The economic and technological development of space will also extend to the outer planets and beyond. The asteroid belt, for instance, holds vast reserves of metals and water that can support space-based industries. Robotic mining missions will become more sophisticated, extracting resources from asteroids and transporting them to manufacturing facilities in orbit. The water from asteroids can be used for both fuel production and life support, making it a critical component in sustaining deep space operations. These developments will create a network of outposts, processing plants, and orbital factories that form the backbone of a growing space economy. Beyond the asteroid belt, the exploration of Jupiter's and Saturn's moons, such as Europa, Enceladus, and Titan, will open up new scientific and colonization opportunities. These moons have diverse and intriguing environments, including subsurface oceans and thick atmospheres, that might harbor conditions suitable for life. Missions to these moons will deploy advanced robotic probes capable of drilling through ice and navigating alien landscapes, searching for signs of life and studying their geological and chemical compositions. Colonies established on these moons would serve as scientific research centers and launch points for missions to even more distant destinations. As humanity pushes further out into the solar system, the need for faster and more efficient propulsion systems becomes paramount. Nuclear fusion propulsion is one of the most promising technologies in development. If achieved, fusion-powered spacecraft could reduce travel times dramatically, making missions to the outer planets and even interstellar destinations feasible within human lifetimes. Fusion propulsion would harness the same reaction that powers the sun, offering a powerful and sustainable energy source for long-distance travel. Researchers are also exploring antimatter propulsion and warp drive concepts that, while still theoretical, could revolutionize space travel by allowing faster-than-light travel or manipulation of space-time itself. Interstellar travel represents the ultimate frontier for humanity. The discovery of potentially habitable exoplanets has captured the imagination of scientists and the public alike. As telescope technology advances, Missions will focus on characterizing these planets, analyzing their atmospheres for signs of life, and studying their climates. The development of interstellar probes, like the proposed breakthrough Starshot, aims to send small, laser-propelled spacecraft to nearby star systems. These missions would provide humanity's first close-up look at planets orbiting other stars, laying the groundwork for future manned missions and possibly even colonization. As we look toward the stars, the discovery of intelligent extraterrestrial civilizations remains one of the most profound possibilities. The search for extraterrestrial intelligence, SETI, continues to scan the cosmos for signals, hoping to detect communication from advanced alien societies. If such a discovery is made, it would challenge humanity's perception of itself and our place in the universe. The implications of contact, whether it is a signal received from a distant civilization or a direct encounter, would be transformative, reshaping science, philosophy, and international relations. Humanity would face the challenge of determining how to respond, how to communicate, and how to navigate the risks and opportunities of interacting with intelligent beings from another world. The potential discovery of life, whether microbial life on Mars or Europa, or intelligent civilizations in distant star systems, prompts humanity to confront deep ethical questions. How should we interact with alien life forms? What are our responsibilities when exploring and potentially colonizing worlds that might harbor life? The need for a new ethical framework for space exploration will grow as our presence expands. This framework will guide humanity's actions, ensuring that exploration and colonization are conducted with respect for alien ecosystems and with consideration for the long-term impact of human activity in space. In the grand story of human expansion, space is more than just a frontier. It is an arena where humanity will redefine its future. The technologies we develop, the societies we build, and the discoveries we make will shape a new chapter in the human narrative, one that extends far beyond Earth. As we establish ourselves on the Moon, Mars, and beyond, we will not only create new homes, but also new ways of thinking, living, and interacting with the universe. The cosmos is an opportunity for growth, cooperation, and transformation, an invitation to expand not just physically, but also intellectually and spiritually. The stars await, offering infinite possibilities for exploration, discovery, and the evolution of humanity itself. As we step into this new era, we carry with us the legacy of our achievements on Earth, but we also face the promise of becoming something greater, a species that transcends its origins, that adapts, innovates, and thrives among the stars. The universe is vast, and as we explore its depths, we will build the foundations of a new civilization, one that reaches beyond the limits of Earth and embraces the boundless potential of the cosmos. As humanity pushes deeper into the cosmos, we begin to witness the unfolding of a new epoch, one that extends beyond the constraints of Earth and embraces the boundless opportunities space offers. The process of building civilizations on other worlds is not just an extension of human life, but a fundamental transformation of society, technology, and culture. Each step into this vast, unexplored frontier demands that we adapt, innovate, and redefine what it means to be human. The development of sustainable habitats, interplanetary trade networks, and new forms of governance will be crucial in this transformation as humanity evolves from a single-planet civilization into a multiplanetary and eventually a galactic presence. The first significant milestone in this expansion will be the transformation of the Moon into a bustling hub of human activity. Lunar bases will evolve into self-sustaining cities, equipped with the infrastructure needed to support life and industry. The use of local resources, such as the extraction of oxygen and water from lunar ice and regolith, will be optimized to reduce dependence on Earth. 3D printing technologies will allow the construction of everything from habitats to machinery using lunar materials. These cities will be equipped with power grids composed of solar arrays, supplemented by nuclear reactors, providing the necessary energy to support life, agriculture, and mining operations. As these lunar cities grow, they will serve as essential hubs for research, commerce, and manufacturing, leveraging their strategic location. Lunar factories will produce materials that are then sent into Earth's orbit or used to build space stations and spacecraft. The Moon's low gravity makes it an ideal launching point for missions to Mars and the asteroid belt, reducing the fuel and energy required compared to launches from Earth. The establishment of orbital platforms and docking stations around the Moon will further support these operations, creating an interconnected system of lunar and orbital infrastructure that facilitates the movement of people and goods. The growth of this lunar economy will set the stage for Mars colonization. The first Martian outposts will focus on exploring the planet's resources and developing the technologies necessary for sustainable living in its harsh environment. The thin atmosphere and high radiation levels make surface living challenging, so initial habitats will be shielded domes or underground structures, utilizing the Martian soil for radiation protection. Over time, these outposts will expand into larger colonies, integrating agriculture, energy production, and industrial capabilities. Solar power, supplemented by nuclear reactors, will provide the energy needed to support these growing cities. One of the most promising aspects of Mars colonization is the potential for terraforming, modifying the planet's environment to make it more Earth-like. While this process would take centuries, scientists are exploring techniques such as releasing greenhouse gases trapped in the Martian soil to warm the atmosphere, building massive mirrors in orbit to reflect sunlight, and even introducing genetically engineered microorganisms to transform the soil. The ultimate goal is to create a breathable atmosphere and liquid water on Mars. But these efforts will require a combination of advanced technology, long-term planning, and international cooperation. Terraforming Mars is not just a technological challenge. It is a massive, collective undertaking that could unite humanity in a shared mission of planetary engineering. Beyond the Moon and Mars, the asteroid belt represents the next frontier for expansion. The vast resources contained in asteroids, metals, water ice, and carbon compounds, are essential for building and sustaining space colonies and industries. Robotic missions to mine these asteroids will be the first step, extracting and processing materials on site. These robotic miners, equipped with AI and autonomous capabilities, will gather resources and transport them to orbital factories or habitats. The asteroid belt will become a network of mining stations and processing centers, creating a flow of materials that supports both Earth-based industries and those in space. The materials harvested from the asteroid belt will be used to build large space habitats and manufacturing hubs in orbit around Earth, Mars, and other strategic locations. These habitats, designed as rotating cylinders or torus structures, will simulate Earth-like gravity and environments, providing comfortable living conditions for large populations. The construction of these habitats will enable the creation of massive space cities, where people live, work, and innovate. These cities will not only support the industrial and scientific development of space, but will also become cultural and social centers, creating new forms of art, entertainment, and education that reflect life in the cosmos. As these space cities grow, the development of interplanetary trade routes will become crucial. A network of transport lanes connecting Earth, the Moon, Mars, and the asteroid belt will facilitate the exchange of resources, goods, and people. Spaceports, positioned strategically throughout this network, will act as hubs for cargo transfer, spacecraft maintenance, and refueling stations. The movement of resources from mining stations to manufacturing facilities, and from farms on Mars to cities on the Moon, will form the backbone of a dynamic space economy. This economy will not only support the expansion of human presence, but will also drive technological and economic growth, benefiting both space colonies and Earth. As humanity establishes itself across multiple celestial bodies, the evolution of governance and political systems becomes a central issue. The colonies and habitats spread throughout the solar system will need their own forms of governance, tailored to the unique challenges and environments they face. On Mars, for example, settlers might form a republic with a constitution that reflects the collaborative and resourceful nature of Martian life. Lunar cities may choose to remain closely aligned with Earth's governments due to their proximity, while asteroid mining communities could develop nomadic or guild-like societies based on resource management and trade. The rise of multiple colonies and settlements in space will eventually necessitate the creation of a unified governing body, such as an interplanetary council or a United Nations of Space. This organization would serve as a forum for cooperation, managing trade agreements, resource rights, and disputes between colonies. It would also establish laws that ensure the fair and sustainable use of space resources, protecting the interests of both Earth-based nations and space communities. The evolution of these political systems will be crucial in maintaining peace, fostering cooperation, and ensuring that space remains a domain for collective progress and innovation rather than conflict and exploitation. The cultural evolution of humanity as it expands into space will be profound. Space colonies will develop their own identities, shaped by their environments and the challenges they face. Martian culture, for example, may emphasize resilience, innovation, and a connection to the planet's landscape, while lunar societies might focus on their strategic role as the crossroads of space trade and exploration. The traditions, holidays, and values that emerge in these societies will be unique, influenced by the isolation of space and the necessity for cooperation. Over generations, these colonies may become entirely distinct from Earth in their customs and outlook, representing the diversity and adaptability of human civilization. The expansion into space will also transform the way humanity thinks about its place in the universe. The discovery of alien life, whether microbial organisms on Europa or signals from distant civilizations, will fundamentally alter our understanding of biology, evolution, and the possibilities of life beyond Earth. Such discoveries will not only be scientific milestones, but also cultural and philosophical events, forcing humanity to reconsider its role as explorers and caretakers of life in the cosmos. The ethical implications of interacting with alien ecosystems and intelligent civilizations will require careful consideration, guiding our approach to exploration and contact. In addition to exploring our solar system, humanity's eyes are set on the stars. The search for exoplanets continues to reveal worlds that may harbor conditions suitable for life. Missions designed to study these planets will use advanced telescopes to analyze atmospheric composition, searching for biosignatures such as oxygen, methane, or water vapor. The discovery of a habitable or even inhabited planet would ignite the next wave of space exploration, interstellar missions. Concepts like generation ships, which could sustain life over centuries as they travel to other star systems, are being explored as long-term solutions for humanity's expansion beyond our solar system. Interstellar travel, however, also brings with it enormous technical, social, and philosophical challenges. The development of propulsion technologies capable of reaching distant stars within a human lifetime is a monumental task. Concepts such as the warp drive, which would manipulate space-time to achieve faster-than-light travel, or antimatter engines, which offer immense energy potential, are still theoretical but represent the forefront of scientific and engineering innovation. If these technologies become feasible, humanity could embark on its first journeys to other star systems, opening up the possibility of colonizing exoplanets and expanding the reach of human civilization. As we contemplate the future of humanity in space, we must also prepare for the transformations that will occur on Earth. The technologies developed for space, from advanced recycling systems to renewable energy sources and AI-driven automation, will have significant applications for Earth's cities and industries. Space exploration will drive innovation in medicine, agriculture, and infrastructure, creating solutions that can improve life on Earth. The knowledge gained from understanding other planets' climates and ecosystems could also enhance our ability to manage and protect Earth's environment, ensuring that our home planet remains a thriving, sustainable part of human civilization. Ultimately, humanity's journey into space is about more than technology and exploration. It is about growth, adaptation, and the evolution of our species. As we step beyond Earth's boundaries, we carry with us not only the legacy of our achievements, but also the responsibility to build a future that reflects the best of human potential. The cosmos invites us to expand our horizons, to create new worlds and societies, and to explore the mysteries of existence on a scale we have never before imagined. The universe is vast, and as we reach into its depths, we embark on a journey that will shape the next chapter of humanity. A chapter where the stars are not just distant points of light, but destinations, homes, and new beginnings for our civilization. As humanity ventures further into the vastness of space, the journey ahead transforms from mere exploration to the deliberate and complex task of building a civilization that spans planets, moons, and beyond. This transition marks a monumental shift, not just technologically, but culturally, socially, and existentially. The universe becomes our new frontier, and with it comes the responsibility to craft a sustainable and ethical presence beyond Earth. As we move from establishing outposts and colonies to developing thriving interplanetary societies, we face both immense challenges and unparalleled opportunities that will redefine the essence of human life. The next major phase of this journey involves establishing permanent, self-sufficient settlements on Mars. These settlements will begin as compact, carefully designed bases capable of supporting small crews. Over time, they will expand into interconnected colonies with hundreds, then thousands of residents. Engineers and architects are developing modular habitat designs that can be scaled up as the population grows, utilizing local resources like Martian soil for construction and natural radiation shielding. These habitats will be designed with redundancy and flexibility, allowing them to adapt as technology improves and as new needs arise within the growing community. To ensure the long-term success of these Martian colonies, we must overcome the challenge of producing sustainable energy. Mars receives less sunlight than Earth, making solar power less efficient, especially during the planet's frequent dust storms, which can darken the skies for weeks or even months. To address this, colonies will rely on a mix of solar energy and small modular nuclear reactors, which can provide consistent power regardless of weather conditions. These reactors, combined with energy storage systems like advanced batteries and hydrogen fuel cells, will create a stable and resilient power grid, crucial for maintaining life support systems, greenhouses, and industrial facilities. Water is another critical resource for Martian colonies. While Mars has water in the form of ice, it is mostly located at the poles or buried beneath the surface. Technologies for extracting and purifying this water are in development, including the use of robotic drills and heat-based methods to melt ice deposits. This water will not only be used for drinking and irrigation, but also for generating oxygen and hydrogen, providing both breathable air and fuel. Water recycling systems, similar to those currently used on the ISS but scaled up and made more efficient, will be integral to ensuring a sustainable supply for expanding colonies. The establishment of agriculture is essential for sustaining a growing population on Mars. Initial efforts will focus on controlled environment agriculture, using hydroponics and aeroponics to grow crops with minimal water and space. These systems allow plants to grow vertically and thrive without soil, using nutrient-rich solutions. As these techniques develop, greenhouses will become more advanced, integrating artificial lighting systems that mimic Earth's day/night cycle and climate control technology to optimize growth conditions. The goal is to create agricultural ecosystems that are diverse, capable of growing a wide range of crops, from staple grains to fruits and vegetables, providing both nutrition and variety for Martian residents. The cultural implications of living on Mars will be significant. Over time, Martian society will develop its own identity, shaped by the challenges and opportunities of life on a new planet. Martians will be pioneers in every sense, living with a heightened sense of cooperation and innovation, as survival depends on the ability to adapt quickly and efficiently. This environment will likely foster a culture that values resourcefulness, scientific curiosity, and a strong sense of community. Martian holidays, traditions, and even art forms will emerge, reflecting the unique conditions of life on Mars and the sense of shared destiny among its inhabitants. As Martian colonies grow, their political structure will begin to evolve. Initially, these settlements may be governed as extensions of Earth-based nations or international coalitions, following protocols set by the agencies or corporations that establish them. However, as these colonies expand and become more self-sufficient, they will likely push for greater autonomy. The desire for local governance will be driven by the need to create laws and policies that reflect the specific realities of Martian life, managing scarce resources, ensuring safety, and maintaining harmony in a tightly knit community where everyone's contribution is critical. The development of a Martian republic or another form of local government could mark the beginning of Mars as an independent entity, distinct from Earth in both governance and identity. Beyond Mars, the Moon continues to play a pivotal role in humanity's expansion into space. As a hub for mining, research, and construction, lunar bases will become increasingly sophisticated, supporting larger populations and more advanced industrial operations. The Moon's low gravity and proximity to Earth make it an ideal location for building and launching spacecraft destined for Mars, the asteroid belt, and beyond. Lunar cities will also serve as critical testing grounds for technologies that will be used on other planets, such as advanced life support systems, autonomous construction robots, and energy solutions. The Moon's resources, particularly its regolith, which contains oxygen and metals, will be crucial in developing an infrastructure that supports human life and industry across the solar system. Asteroid mining will become a key component of humanity's space economy. Robotic missions will initially target near-Earth asteroids rich in metals like platinum, gold, and nickel, as well as water ice. These resources will be extracted, processed, and transported to orbital refineries and manufacturing stations. The water from these asteroids will be used for both fuel production and life support, while the metals will be utilized in the construction of space habitats, ships, and stations. As mining technology advances, larger-scale operations will move into the asteroid belt, creating a vast network of robotic and human-operated facilities that support the growth of colonies on Mars, the Moon, and even farther into the solar system. The expansion into the outer solar system will bring new challenges and discoveries. Jupiter's and Saturn's moons, such as Europa, Callisto, Titan, and Enceladus, offer a variety of environments, some of which may harbor the conditions necessary for life. Europa, with its subsurface ocean beneath a thick ice crust, is a primary target for exploration. Missions will deploy advanced robotic probes capable of drilling through the ice and releasing autonomous submersibles to explore the ocean beneath. These missions seek to uncover signs of microbial life, which would revolutionize our understanding of biology and the potential for life beyond Earth. Titan, Saturn's largest moon, presents another unique environment. Its thick atmosphere and surface lakes of methane and ethane suggest a complex climate system. Dragonfly, a planned rotorcraft mission, will explore Titan's surface, studying its chemistry and searching for prebiotic molecules that could reveal the building blocks of life. If conditions allow, future missions could establish small research bases on Titan, where scientists would study the Moon's atmosphere, geology, and potential for supporting life. These bases would serve as platforms for understanding one of the most Earth-like environments outside our planet, albeit with vastly different chemistry. The outer reaches of the solar system, including Uranus, Neptune, and their moons, remain largely unexplored. Missions to these distant planets will utilize advanced propulsion systems, such as nuclear, electric, or fusion propulsion, to reduce travel time and increase the payload capacity of spacecraft. These missions will focus on studying the gas giants' atmospheres, magnetic fields, and moons, particularly Triton, a moon of Neptune that shows signs of active geysers and subsurface activity. Colonies in these regions would be research outposts and could play a role in exploring the Kuiper Belt and beyond. As humanity establishes a presence throughout the solar system, the need for efficient and sustainable interplanetary travel will become more pressing. The development of fusion propulsion, which uses the same principles that power the sun, promises to revolutionize space travel. Fusion engines could provide the thrust needed for fast travel between planets, reducing journey times from months to weeks. This technology would not only facilitate the movement of people and goods, but also enable the rapid response to emergencies or the deployment of large-scale projects, such as the construction of interplanetary spaceports and refueling stations. In addition to fusion propulsion, researchers are exploring exotic propulsion methods like antimatter drives, and even concepts like the Alcubierre warp drive, which theoretically allows faster-than-light travel by bending space-time. While these technologies remain in the realm of theory and experimentation, they represent the cutting edge of our efforts to overcome the vast distances of space. If realized, these propulsion systems could make interstellar travel a possibility, allowing humanity to explore and potentially colonize exoplanets and other star systems. The search for habitable exoplanets and the possibility of interstellar travel fuels humanity's drive to understand its place in the universe. As telescopes like the James Webb Space Telescope and future observatories analyze the atmospheres of distant planets, the discovery of biosignatures could indicate that life is widespread in the galaxy. Such a discovery would transform our understanding of biology and evolution, opening up new fields of study and possibilities for future missions. If habitable or inhabited worlds are found, they will become the next targets for humanity's expansion, setting the stage for humanity's eventual move beyond the solar system. Interstellar missions would require not only advanced technology, but also a new approach to human life. The concept of generation ships, massive self-sustaining spacecraft that could support life for centuries as they travel between stars, represents one possible solution. These ships would be fully equipped with ecosystems, agriculture, and infrastructure to sustain large populations over long periods. The societies formed aboard these generation ships would likely be entirely distinct, developing their own cultures, governance, and ways of life as they move through the vast distances between stars. The potential discovery of intelligent extraterrestrial civilizations would be a watershed moment for humanity. Whether through direct contact or the detection of distant signals, such an event would force us to confront deep questions about our place in the cosmos, our origins, and the future of our species. How we respond to this discovery, whether with curiosity, caution, or a desire for cooperation, will shape the trajectory of human civilization. The implications for science, philosophy, religion, and global unity would be profound, as humanity grapples with the reality that we are not alone. In this vast cosmic theater, humanity's journey is one of transformation. The challenges we face as we expand into space, adapting to new environments, building sustainable ecosystems, and interacting with potential alien life, will test our ingenuity, resilience, and unity. Each new frontier brings the promise of discovery and the opportunity to build something greater, expanding not just our physical presence, but our understanding of life and existence itself. The universe offers us the chance to evolve beyond the limits of Earth, to explore, innovate, and create civilizations that reach the stars. As we embrace this future, the cosmos becomes our home, and the story of humanity unfolds across the vast expanse of space, an epic journey of discovery, adaptation, and the forging of a new destiny among the stars. As humanity continues its bold expansion into the cosmos, the reality of living and thriving in space becomes increasingly complex and dynamic. We are no longer simply explorers. We are pioneers building the foundation of a multi-planetary civilization, a society that not only reaches beyond Earth, but thrives in the diverse environments of the solar system and beyond. Each step forward brings new challenges, technologies, and opportunities that reshape our understanding of life and push the boundaries of what is possible. The evolution of space colonies, the development of advanced propulsion systems, and the potential discovery of extraterrestrial life all contribute to a future where humanity's presence in space is both permanent and transformative. The foundation of this transformation lies in the construction and growth of self-sustaining colonies on the Moon and Mars. On the Moon, cities will emerge as vital hubs of commerce, research, and industry, providing the necessary infrastructure to support humanity's deeper ventures into space. These lunar cities will rely heavily on the Moon's resources, with advanced mining operations extracting valuable materials from the lunar surface. Regolith, the Moon's surface dust, will be processed to produce oxygen and metals, while lunar ice deposits will provide water for human consumption, agriculture, and rocket fuel. These resources will enable the Moon to become a launch pad for missions to Mars, the asteroid belt, and the outer planets, reducing the costs and logistical challenges of launching from Earth. As lunar colonies become more advanced, they will not only support human life, but also drive scientific progress and technological innovation. Research centers on the Moon will study the effects of low gravity on human biology, test advanced materials for space construction, and develop technologies that can be applied to both Earth and Mars. The Moon's proximity to Earth makes it an ideal location for testing these innovations, and the insights gained will be crucial for the success of more distant colonies. Additionally, the Moon's far side offers a perfect vantage point for building radio telescopes shielded from Earth's radio interference, providing humanity with unprecedented views of the cosmos and allowing us to peer deeper into the universe's mysteries. Meanwhile, Mars will continue to develop as a frontier of human settlement and technological advancement. The establishment of Martian colonies will require robust and sustainable life support systems capable of functioning in the planet's harsh environment. Greenhouses designed to operate under Martian conditions will utilize hydroponics and vertical farming techniques to maximize crop yields in limited space. These farms will not only provide food, but also produce oxygen through photosynthesis, contributing to the overall life support system of the colony. Engineers are also developing bioreactors that utilize algae and bacteria to recycle waste and generate essential nutrients, creating a closed-loop ecosystem that supports human life far from Earth. Martian architecture will evolve to include both underground and above-ground structures, designed to protect inhabitants from radiation and extreme temperatures. These habitats will use a combination of Martian soil and 3D printed materials to create durable and insulated environments. Over time, entire Martian cities could emerge, connected by underground networks that protect residents from dust storms and radiation while allowing efficient transportation and resource management. The development of modular architecture will enable rapid expansion and flexibility, allowing these cities to grow organically as more settlers arrive and technology evolves. The governance of Martian colonies will become a central issue as these settlements expand. Initially governed as outposts of Earth-based nations or international consortia, Martian colonies will eventually seek greater autonomy. The unique conditions of life on Mars, such as the need for constant cooperation, resource management, and adaptation, will foster a distinct sense of identity among its inhabitants. These settlers, who must work together closely to survive and thrive, may develop their own political and social systems, suited to the realities of Martian life. As they become more self-sufficient, Martian colonies will push for self-governance, potentially forming their own republics or federations with constitutions that emphasize the values of cooperation, sustainability, and innovation. Beyond Mars, the establishment of a network of asteroid mining stations will play a crucial role in humanity's expansion. The resources found within asteroids, metals, water ice, and carbon compounds, are essential for building and maintaining space colonies, as well as for constructing spacecraft and habitats. Autonomous robotic miners will be the first to operate in the asteroid belt, extracting these resources and transporting them to refineries positioned in orbit around Earth, Mars, and other key locations. The development of these mining stations will create a flow of materials that supports the growth of colonies throughout the solar system, while also generating significant economic opportunities. The asteroid belt will not only provide raw materials, but also become a hub of industrial activity. Space foundries, using metals extracted from asteroids, will manufacture components for space stations, habitats, and interplanetary spacecraft. These facilities will produce everything from structural parts to electronics, reducing the need to transport heavy or complex items from Earth. As these capabilities grow, the solar system will become a complex web of resource extraction, manufacturing, and trade, with Mars, the Moon, and asteroid bases forming the backbone of an interplanetary economy. The establishment of interplanetary trade routes will require the development of efficient transportation and refueling networks. Spaceports positioned strategically in orbit around Earth, the Moon, Mars, and within the asteroid belt will serve as critical hubs for cargo and passenger transfers. These ports will provide essential services, including spacecraft maintenance, refueling using resources extracted from the Moon and asteroids, and housing for travelers. The evolution of this infrastructure will transform space travel into a routine activity, enabling a constant flow of goods and people between colonies and further integrating the solar system into a cohesive economic system. As humanity's presence expands throughout the solar system, the development of faster propulsion technologies becomes increasingly critical. Fusion propulsion, with its potential to significantly shorten travel times between planets, represents a transformative technology in this regard. Fusion engines, which use reactions similar to those that power the Sun, could enable spacecraft to travel between Earth and Mars in weeks rather than months, and to the outer planets in a fraction of the time currently required. Fusion-powered spacecraft will not only facilitate exploration, but also make emergency response missions and the transportation of large-scale cargo more efficient, supporting the rapid development of colonies. The success of fusion propulsion could lay the groundwork for even more advanced technologies, such as antimatter drives and warp drives. While these concepts remain largely theoretical, research into the manipulation of space-time and the harnessing of exotic forms of energy is ongoing. If such technologies become feasible, they could revolutionize our ability to explore the galaxy, making interstellar missions possible within human lifetimes. The prospect of reaching other star systems, such as Alpha Centauri, would mark the beginning of humanity's transition from a multiplanetary civilization to an interstellar one, opening up new realms of possibility and expanding our reach across the cosmos. The search for habitable exoplanets remains a driving force in this exploration. As technology improves, missions will be able to conduct detailed studies of planets orbiting other stars, analyzing their atmospheres for signs of water, oxygen, and other potential biosignatures. The discovery of a habitable, or even inhabited, exoplanet would ignite the next wave of space missions, focusing on closer examination and, eventually, interstellar travel. Humanity's exploration of these distant worlds could lead to the establishment of new colonies on exoplanets, each becoming a seed for new civilizations and cultures, spreading the influence of human life across the galaxy. As humanity spreads into the cosmos, the potential for encountering intelligent extraterrestrial civilizations remains a profound and complex possibility. The discovery of such civilizations, either through direct contact or the detection of distant signals, would transform our understanding of life, intelligence, and our place in the universe. How we choose to engage with these civilizations, whether through peaceful communication, cautious observation, or active collaboration, will shape the future of humanity and our relationship with the cosmos. The implications for global society, politics, and philosophy would be immense, prompting us to rethink concepts of identity, cooperation, and unity on an interplanetary scale. The possibility of encountering alien life also brings with it significant ethical considerations. Humanity must develop guidelines for interacting with extraterrestrial ecosystems, ensuring that our expansion does not harm or disrupt alien biospheres. The principles of planetary protection, preventing both forward contamination, spreading Earth-based life, and backward contamination, introducing alien organisms to Earth, will need to be expanded and enforced rigorously as our presence in space grows. These ethical frameworks will guide how humanity interacts with other worlds, ensuring that exploration is conducted responsibly and sustainably. On Earth, the advancements driven by space exploration will have profound impacts as well. Technologies developed for space, such as efficient recycling systems, renewable energy solutions, and medical innovations, will be applied to address global challenges like climate change, resource scarcity, and public health. The economic growth generated by the space economy will create new industries and job opportunities, influencing the global economy and enhancing technological progress. Moreover, the perspective gained from living and working in space will foster a greater sense of unity among humanity, as people begin to see themselves not just as citizens of individual nations, but as part of a shared, interconnected species exploring the universe together. Culturally, the spread of human life throughout the cosmos will create new forms of art, literature, and traditions that reflect the diverse experiences of space colonists. Stories of life on Mars, the Moon, or space habitats will inspire new narratives, and the creation of new cultural forms will help bridge the gap between Earth and its colonies. Festivals, music, and visual arts that celebrate the challenges and triumphs of space living will evolve, forming a rich tapestry of human expression that reflects our journey across the stars. Ultimately, humanity's expansion into space is a story of transformation and evolution. As we establish colonies, develop new technologies, and encounter new forms of life, we will not just be extending our reach, we will be changing who we are. The process of becoming a multiplanetary and eventually an interstellar civilization will redefine our identity, pushing us to adapt, innovate, and grow in ways that transcend the limitations of our past. The universe is vast, and as we explore its depths, we will build new worlds, create new societies, and forge a future that reflects the boundless potential of the human spirit. The cosmos is not just a destination. It is the stage for humanity's greatest adventure. The challenges we face and the discoveries we make will shape the next chapter of our civilization, as we move from being inhabitants of a single planet to architects of an interconnected, multi-world society. The stars await, and with them, the promise of a new era, a time when humanity's story unfolds not only on Earth but across the universe, driven by our unyielding curiosity, resilience, and quest for knowledge. As humanity continues its journey beyond Earth, venturing deeper into the solar system and beyond, the transformation from a single-planet species to a multi-planetary civilization becomes a reality, unfolding through ambitious projects, technological breakthroughs, and the birth of new societies. Each milestone in this journey represents a fusion of human ingenuity, resilience, and adaptability as we face unprecedented challenges and opportunities that will reshape life as we know it. The stars are no longer distant points of light. They become our destinations, our future homes, and the canvas upon which we will paint the next chapter of human civilization. The establishment of permanent lunar and Martian colonies lays the foundation for this transformation. On the Moon, colonies will evolve from small outposts into thriving cities that serve as hubs for research, mining, and manufacturing. The Moon's resources, including metals and water ice, will be critical for constructing habitats, producing rocket fuel, and supporting life. Lunar regolith will be processed into building materials and used to 3D print structures, minimizing the need for transporting supplies from Earth. These lunar cities will become centers of innovation, testing technologies that will eventually be deployed on Mars and beyond. They will also serve as important refueling and maintenance stations for missions venturing farther into the solar system. The Moon's close proximity to Earth makes it an ideal staging ground for the development of space-based industries. Orbital shipyards will manufacture spacecraft and satellites, using materials mined from the Moon and asteroids. These shipyards will become critical to the expansion of space infrastructure, building everything from Mars-bound habitats to advanced spacecraft for deep space exploration. The growth of these industries will create a booming economy that connects Earth, the Moon, and the rest of the solar system, making the lunar surface a dynamic and strategic point in humanity's expansion. Meanwhile, Mars remains the primary focus for human colonization beyond the Moon. The Martian colonies will initially be established in locations rich in resources, such as ice deposits and mineral-rich soils. These colonies will use cutting-edge technology, including autonomous construction robots, to build habitats that are not only safe and sustainable, but also scalable. Early habitats will be modular, designed to expand as the population grows and as infrastructure needs increase. As these habitats evolve, they will integrate agricultural systems that combine hydroponics, aeroponics, and vertical farming, maximizing food production in limited space and utilizing minimal water. One of the most critical technological challenges for Martian colonies will be developing reliable and robust energy systems. Given the limitations of solar power on Mars, due to frequent dust storms and the planet's distance from the Sun, these colonies will rely heavily on small nuclear reactors. Advanced versions of these reactors will provide continuous power, supporting the life support systems, agricultural modules, and industrial processes necessary for a thriving colony. Additionally, Experiments with wind turbines designed to function in Mars' thin atmosphere may supplement these power systems, taking advantage of the planet's strong winds. The growth of Martian cities will bring about the need for efficient transportation networks to connect different regions and facilitate the movement of people and resources. Rovers and high-speed, magnetically propelled trains could be developed to travel through underground tunnels, shielding them from the planet's harsh surface conditions. These transportation networks will not only connect habitats, but also link mines, greenhouses, and industrial centers, creating a cohesive infrastructure that supports the colony's economic and social growth. As Martian cities grow, their inhabitants will develop a sense of identity distinct from Earth, fostering a unique Martian culture. This culture will be influenced by the need for collaboration, adaptability, and resilience as settlers work together to solve the challenges of living on Mars. Over time, Martian traditions, holidays, and social customs will emerge, reflecting both the achievements and the hardships of life on the Red Planet. Festivals celebrating the milestones of Martian agriculture, the anniversary of the first human landing, or the day when a new city is founded may become annual events that unite the Martian population, fostering a sense of community and belonging. The evolution of Martian governance will also be a significant development. Initially, these colonies may be governed under the jurisdiction of Earth-based entities or international coalitions. However, as the colonies grow in size and capability, the desire for autonomy will become inevitable. The unique challenges and conditions of Martian life will necessitate the creation of new political systems that are tailored to the realities of living on another planet. Martians may form independent republics with democratic systems that emphasize collaboration and resource management. This political evolution will be marked by the drafting of a Martian constitution, reflecting the values of sustainability, innovation, and cooperation that are central to life on Mars. Beyond Mars, the asteroid belt represents a vast reservoir of resources that will be crucial for the continued expansion of human civilization. Robotic mining operations will be deployed to harvest these resources, targeting asteroids rich in metals like platinum and nickel, as well as those containing water ice. These robotic miners will operate autonomously, extracting materials and transporting them to refineries positioned strategically within the asteroid belt and in orbit around planets like Mars and Earth. The success of these missions will not only support the construction of space habitats and spacecraft, but also fuel the growth of a new space economy, one that connects the various colonies and industrial hubs throughout the solar system. The resources extracted from asteroids will support the construction of large space habitats in orbit around Earth, Mars, and the Moon. These habitats, designed as rotating cylinders or torus structures, will create artificial gravity, enabling Earth-like living conditions for large populations. Inside these habitats, ecosystems will be established that include forests, lakes, and agricultural zones, providing not only food and oxygen, but also a sense of nature and normalcy for the inhabitants. These space habitats will become cities in their own right, complete with schools, hospitals, and cultural centers, serving as both residential and commercial hubs for space travelers and permanent residents. As space habitats and colonies flourish, the development of efficient transportation systems will be crucial to connect these distant locations. The deployment of fusion-powered spacecraft will be a transformative step. Fusion propulsion technology, leveraging the power of nuclear fusion to produce vast amounts of energy, could drastically reduce travel times between planets, making journeys that currently take months possible in weeks. These fusion-powered vessels will be used not only for cargo transport, but also for passenger travel, making the movement of people between Earth, Mars, and other colonies routine. The establishment of spaceports in orbit and on planetary surfaces will support this growing transportation network, providing refueling stations and maintenance facilities that keep interplanetary travel safe and efficient. While Mars and the Moon serve as the focal points for early colonization efforts, the outer solar system remains a vast frontier filled with scientific and colonization opportunities. Missions to Jupiter's moons, such as Europa, Ganymede, and Callisto, will aim to explore the possibility of life in these icy environments. Europa, with its subsurface ocean beneath a thick ice crust, presents one of the most promising targets for the search for extraterrestrial life within our solar system. Advanced robotic probes will drill through the ice and release submersibles to explore Europa's ocean, searching for signs of microbial life and studying the chemistry of this alien environment. Saturn's moon Titan, with its thick atmosphere and hydrocarbon lakes, offers another intriguing possibility. Titan's surface conditions are unlike anything on Earth, yet the potential for prebiotic chemistry makes it a valuable target for exploration. Missions like NASA's Dragonfly, a drone designed to explore Titan's landscape, will gather data on its atmosphere and surface composition, searching for signs of chemical processes that could lead to life. If these missions are successful, research outposts could be established on Titan, serving as platforms for long-term scientific study and as bases for further exploration of the outer solar system. The expansion into the outer solar system will require advances in propulsion technology beyond what is currently available. Nuclear electric propulsion systems, which use nuclear reactors to generate electricity for ion thrusters, offer a promising method for reaching these distant targets. These systems provide a steady, efficient thrust over long periods, making them ideal for missions to Jupiter, Saturn, and beyond. The development of these technologies will enable the exploration of Uranus, Neptune, and the Kuiper Belt, opening up new frontiers and potentially revealing more about the formation of the solar system and the distribution of resources on its outskirts. As humanity expands into these remote regions, the possibility of establishing colonies on moons like Enceladus, Ganymede, or Triton becomes a reality. These moons, with their unique environments and potential for subsurface oceans, will be studied for their habitability and resource potential. Colonies in these regions would initially be research-focused, but over time, they could evolve into permanent settlements supporting life and industry. These outposts would also serve as launch points for missions that explore the Kuiper Belt and the distant edges of the solar system, pushing humanity's reach even further. Beyond the solar system, the search for exoplanets and the possibility of interstellar travel remain humanity's ultimate goals. The detection of biosignatures or even technosignatures, evidence of advanced technology, on distant exoplanets would be a transformative discovery. Such a find would not only confirm that life exists beyond Earth, but also motivate the development of propulsion systems capable of reaching these distant worlds. Concepts like the Breakthrough Starshot Initiative, which proposes sending tiny, laser-propelled probes to nearby star systems, represent the initial steps toward making interstellar travel a reality. As humanity contemplates interstellar travel, the development of generation ships or advanced propulsion systems like antimatter drives or warp technology will become essential. Generation ships, designed to sustain human life over centuries as they travel between stars, would carry entire communities, creating mobile societies that evolve independently of Earth. These ships would be self-sustaining ecosystems, capable of producing food, recycling resources, and maintaining a stable environment over long periods. The societies aboard these vessels would develop their own cultures, traditions, and governance systems as they journey through the vast distances between stars. The encounter with an intelligent extraterrestrial civilization, should it happen, would profoundly impact human society. Whether this contact is established through communication signals or direct exploration, the implications for science, philosophy, and global unity would be immense. Humanity would face the challenge of interpreting alien languages, understanding their technologies, and deciding on how to engage with beings whose motivations and intentions are unknown. The response to this discovery could either unite humanity in a shared mission or provoke divisions, depending on how the encounter is managed. The ethical considerations of humanity's expansion into space are equally important. Ensuring that our presence does not disrupt potential ecosystems or harm alien environments will require strict guidelines and global cooperation. Humanity must develop and adhere to principles that respect the intrinsic value of extraterrestrial life, whether it is microbial organisms on Europa or more complex forms on exoplanets. These ethical frameworks will guide humanity's interactions with alien worlds, ensuring that our expansion is conducted responsibly and sustainably. The universe is vast, and as humanity spreads its influence beyond Earth, the opportunity to become a truly interplanetary and eventually interstellar civilization emerges. Each new frontier challenges our technology, governance, and culture, pushing us to adapt and innovate. As we establish colonies, create new societies, and explore the unknown, we will build a future that reflects the boundless potential of the human spirit. A future where the cosmos becomes not just our destination but our home. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe and see you on our next interstellar trip.